In the beginning there was darkness, endless, infinite, stretching beyond the reach of thought, beyond the grasp of imagination. And yet, within that vast silence, stars ignited, tiny sparks in the void, islands of light in a sea of nothingness. Each one a sun, each one a possibility. Somewhere, in the immensity of the cosmos, life stirred. Somewhere, meaning began to take shape against the cold, indifferent universe. We are born into this enormity, brief flickers of awareness adrift on a pale blue planet. Our lives, our struggles, our dreams, they are infinitesimal in scale, yet profound in impact. For in the shadow of infinite galaxies, we glimpse our own potential. We confront the fragility of existence and discover the power to imagine, to create, to transcend. The universe is vast. Its mysteries are endless. And yet, in that boundless expanse, we find the spark that drives us forward, the courage to explore, the hunger to understand, the quiet whisper that urges us to reach for something great. Every discovery, every question, every step beyond the known is a reminder, though small, we are capable of meaning, of impact, of wonder. And so we look upward, not just to see, but to understand, not just to exist, but to become. For in the infinite, in the cosmic, in the unknown, lies the ultimate challenge and the ultimate opportunity for life, for consciousness, for humanity. The universe waits, and we are ready. The James Webb signal, why this planet changed everything. For centuries, humanity has looked up at the night sky and wondered whether we are alone. That question has never been idle curiosity. It has shaped religions, inspired art, fueled science, and quietly haunted our sense of meaning. Every generation inherits it, reframes it with new tools, and passes it forward. Yet for all our progress, the universe has remained stubbornly silent, vast, beautiful, and indifferent. Until now, when the James Webb Space Telescope began transmitting its first data, scientists expected surprises. What they did not expect was a signal so precise, so statistically compelling, that it would force a fundamental shift in how we think about life beyond Earth. This was not a blurry image or a speculative anomaly. It was a planetary fingerprint etched in light, passed through physics, and measured with a confidence that bordered on unsettling. A 99.7% probability is not certainty, but in science it is a thunderclap. This moment did not arrive suddenly. It was decades in the making, built on quiet persistence, incremental advances, and a collective refusal to accept that we might never know. The James Webb Telescope itself is a monument to long-term thinking. Designed in the late 1990s, delayed by engineering challenges and budget overruns, doubted by critics, and launched amid global uncertainty, it represents something increasingly rare, a civilization willing to invest in knowledge that may not pay off immediately, or even within a single lifetime. Webb does not look at the universe the way our eyes do. It sees in infrared, a realm where heat becomes information and ancient light tells its story. This ability allows it to peer through cosmic dust, to look deeper into nebulae where stars are born, and to analyze the atmospheres of planets orbiting distant stars. It does not merely observe, it interrogates. Every photon it captures is a question answered, a hypothesis tested, a mystery narrowed. The planet that changed everything does not look remarkable at first glance. It does not announce itself with spectacle. It does not glow brighter than its neighbors or sit alone in cosmic isolation. It simply orbits its star at the right distance, with the right size under the right conditions, and with an atmosphere that tells a story no planet has told us before. When Webb analyzed the starlight passing through this planet's atmosphere, it found a chemical imbalance that should not exist in a dead world. Certain gases, when present together, are unstable. They react, neutralize, disappear. On Earth, their continuous presence is sustained by life. Microbes, plants, and complex organisms constantly replenish them, maintaining a fragile chemical tension. Without biology, the atmosphere would settle into equilibrium. Silence, stillness, death. But this planet was not silent. The signal suggested active processes, ongoing renewal, a system refusing equilibrium. Scientists did not rush to declare life. They ran the data through models, cross-checked assumptions, questioned instruments, and invited skepticism. Extraordinary claims demand extraordinary evidence, and the scientific community knows this better than anyone. What emerged was not a declaration, but a probability, calculated, constrained, and deeply uncomfortable in its implications. A 99.7% chance does not mean we have found aliens. It means something far more profound. The universe has crossed a threshold where life is no longer a philosophical question alone. It is an empirical one. For most of human history, life has been a singular event in our understanding. Earth was not just our home, it was the exception. Even as science expanded our knowledge of galaxies and stars, life remained localized, precious, and improbably rare. The so-called rare Earth hypothesis argued that complex life required such a precise chain of events that it might never occur again. In that framework, humanity carried a cosmic burden. We were not just inhabitants of the universe, but its only witnesses. The James Webb signal destabilizes that idea. If life can arise under different conditions around different stars, in atmospheres unlike our own, then biology is not a fluke. It is a tendency, a process woven into the fabric of cosmic evolution, emerging wherever chemistry, energy, and time intersect in the right way. This does not diminish humanity. It contextualizes us, and context changes everything. The discovery forces us to confront a deeper truth. The universe is not just expanding outward, it is becoming more complex over time. From simple particles to atoms, from atoms to molecules, from molecules to cells, and from cells to consciousness. There is a pattern of increasing organization. Life may not be an accident. It may be what the universe does when given enough opportunity. This idea has unsettling consequences. If life is common, then intelligence may be common. And if intelligence is common, then civilizations may rise, struggle, adapt, or collapse across the galaxy. The silence we have observed, the absence of clear signals from other intelligent beings becomes more troubling, not less. It raises the question of not just where everyone is, but what happens to civilizations over cosmic timescales. Yet, the James Webb signal is not about fear. It is about perspective. For the first time, humanity is not merely speculating about life elsewhere. We are measuring it. We are assigning probabilities. We are narrowing uncertainty. That shift from wonder to evidence marks a new era in human self-understanding. It is the difference between myth and history, between belief and knowledge. This discovery arrives at a critical moment. We live in an age of fragmentation, short attention spans, and accelerating crises. Climate change, geopolitical instability, and technological disruption dominate our narratives. Against this backdrop, a distant planet might seem irrelevant. But it is precisely now that such a discovery matters most, because it reminds us that our problems, while urgent, are not the sum total of existence. The universe is 13.8 billion years old. The light analyzed by James Webb began its journey long before humans built cities, wrote laws, or imagined nations. It traveled through expanding space, past collapsing stars and forming galaxies, only to be captured by a fragile instrument built by a species still arguing about its place in the world. That perspective does not make our struggles meaningless. It makes our choices significant. If life is emerging elsewhere, then the universe is not indifferent to complexity. It is permissive of it, and that implies responsibility. We are no longer just survivors on a lonely rock. We are participants in a larger story of cosmic evolution. How we treat our planet, how we manage our technology, and how we choose to cooperate or destroy each other may determine whether we become a brief experiment or a lasting presence. The James Webb signal also reframes the future of exploration. For decades, science fiction imagined discovery as a dramatic encounter. Spaceships, signals, contact. Reality is quieter, more subtle, and more powerful. It comes in spectra and probabilities, in patient analysis rather than cinematic revelation. And yet, it is no less transformative. This planet may never be visited. Its inhabitants, if they exist, may never know us. But the knowledge of their possible existence changes us. It forces humility. It challenges exceptionalism. It invites curiosity rather than conquest. There is also a psychological dimension to this moment that cannot be ignored. Humans are meaning-making creatures. We define ourselves by stories about origins, destinies, and uniqueness. The idea that life exists elsewhere disrupts some stories while enriching others. It asks us to mature as a species, to let go of the comfort of singularity and embrace the dignity of participation. In this sense, the James Webb signal is not just a scientific finding, it is a mirror. It reflects our capacity for patience, cooperation, and imagination. Thousands of scientists across continents contributed to this mission. Governments funded it, not for profit, but for knowledge. Engineers solved problems they could not fully test until the telescope was already in space. This is what humanity can do when it thinks beyond the immediate. And that may be the most hopeful signal of all. The planet with a 99.7% chance of life does not answer all our questions. It raises better ones. What forms can life take? How does intelligence emerge? What are the limits of adaptation? And perhaps most importantly, what kind of civilization do we want to be if we are not alone? The universe has not spoken to us in words. It has spoken in light. And for the first time, we are beginning to understand the message. This is why this planet changed everything. Not because it confirms what we hoped or threatens what we feared, but because it expands what it means to be human. We are no longer asking the question from ignorance. We are asking it from the edge of discovery. And that is where history begins. 2.99.7% probability. How scientists measure life. When scientists say 99.7% probability, they are not making a dramatic claim for attention. They are doing something far more disciplined and in many ways more radical. They are translating uncertainty into structure. They are admitting what they do not know, defining the boundaries of that ignorance, and then narrowing it with evidence. To understand why this number matters, we first have to understand how science approaches the idea of life itself. Life is not a single thing. It is not a shape, a color, or a species. It is a process. On Earth, life is chemistry organized against entropy. It is matter that resists equilibrium, energy that flows through structured systems, and information that replicates with variation. Cells divide, ecosystems evolve, and atmospheres change because life is active, not passive. This activity leaves traces, and those traces, not organisms themselves, are what we search for across the cosmos. Scientists cannot point a telescope at a distant planet and see forests or oceans. What they can see is light. Starlight passes through a planet's atmosphere, interacts with its molecules, and arrives altered. Certain wavelengths are absorbed, others pass through, and the resulting spectrum becomes a chemical signature. This is not guesswork, it is physics, tested in laboratories, refined over generations, and now applied on a cosmic scale. Every molecule absorbs light in a unique way. Water vapor, carbon dioxide, methane, oxygen, ozone, all leave distinct fingerprints. By analyzing these patterns, scientists can determine not just what gases are present, but how much of each exists, how they interact, and whether their coexistence makes sense under known physical laws. This is where probability enters the conversation. On a lifeless planet, atmospheric chemistry trends toward balance. Volcanoes release gases. Sunlight breaks molecules apart. Gravity pulls heavier elements downward. And over time, reactions settle into predictable states, without an active process constantly disrupting this balance. Unstable combinations disappear, they cannot persist. Life, however, is disruption made systematic. On Earth, oxygen is a prime example. It is highly reactive. Left alone, it would bind with other elements and vanish from the atmosphere. The only reason it remains abundant is because photosynthetic organisms continuously produce it. Methane is another example. It breaks down quickly under sunlight. Its presence in large quantities requires constant replenishment. On Earth, that replenishment comes largely from biological sources. When scientists detect gases like these together, especially in combinations that should not coexist, they pay attention, not because they want to find life, but because physics tells them something unusual is happening. The 99.7% probability does not come from a single observation. It emerges from layers of analysis. First, instruments collect raw data, then that data is cleaned, calibrated, and corrected for noise, stellar activity, instrumental drift, cosmic interference. Every possible source of error is modeled and accounted for. What remains is a signal, but even then, interpretation is cautious. Scientists build models of planetary atmospheres under different conditions. They simulate lifeless worlds with varying temperatures, pressures, and chemical compositions. They test scenarios involving volcanism, lightning, ultraviolet radiation, and exotic geochemistry. Each model asks the same question: can this atmosphere exist without life? Most fail. The few that succeed require extreme assumptions, conditions so rare or unstable that their likelihood drops sharply. When all known non-biological explanations are tested and weighed, what remains is not certainty, but probability, a measure of how likely life is compared to all other explanations. This is the origin of the 99.7% figure. It means that given current knowledge, given observed data, and given the full range of tested alternatives, life is the most plausible explanation by a wide margin, not the only explanation, but the most consistent one. This approach reflects the humility of science. Scientists do not claim absolute truth, they update beliefs as evidence changes. Probability is not weakness, it is rigor. It allows conclusions to evolve rather than collapse. There is another layer to this measurement that often goes unnoticed. Scientists are not looking for life as we know it, they are looking for life as we can recognize it. That distinction matters deep. Life elsewhere may not use DNA. It may not breathe oxygen or rely on liquid water in the same way we do. But it must still obey thermodynamics. It must still process energy, maintain structure, and interact with its environment. Those interactions leave signatures. While biology can vary, physics does not. This is why atmospheric disequilibrium is so powerful. It is not Earth-centric. It is principle-based. It asks whether a planet is chemically restless in a way that suggests ongoing activity. Life, regardless of form, is restless. Probability also incorporates time. A snapshot of an atmosphere is not enough. Scientists consider how long a given combination of gases can persist. If a molecule breaks down in thousands of years but is still abundant, something must be replenishing it. If a planet has existed for billions of years, short-lived gases should be gone unless actively maintained. This temporal reasoning transforms observation into inference. It allows scientists to reconstruct invisible processes from visible evidence. In this sense, the search for life is less about discovery and more about detective work on a cosmic scale. The number 99.7% also reflects consensus, not authority. It is not declared by a single scientist or institution. It emerges through peer review, replication, and critique. Teams challenge each other's assumptions, reanalyze data, and attempt to falsify conclusions. If an explanation survives this process, its credibility grows. This is why such a probability carries weight. It has been stress-tested. Yet, even here, restraint remains. Scientists avoid declaring life found because probability is not proof. A single unknown process could still exist. Nature has surprised us before. But probability changes how we frame the question. Instead of asking, could there be life? We begin asking, what kind of life might this be? That shift is profound. It moves the conversation from existence to diversity, from isolation to distribution, from philosophy to emerging biology. There is also a human dimension to probability that deserves attention. Humans are uncomfortable with uncertainty. We crave definitive answers, but the universe rarely provides them. Science does not eliminate uncertainty. It disciplines, it teaches us how to live with incomplete information without surrendering to ignorance. In many ways, this mirrors life itself. We make decisions without guarantees. We weigh evidence, assess risk, and act under uncertainty. The scientific method formalizes this process. It is not just a tool for discovery, it is a mindset. The measurement of life through probability reflects a mature civilization, one that understands knowledge as provisional, truth as asymptotic, and progress as cumulative. It is the opposite of dogma. It invites revision, not reverence. This matters because the discovery of probable life elsewhere will challenge deeply held beliefs. Cultural narratives often rely on certainty about origins, purpose, and uniqueness. Probability does not attack these narratives directly. It erodes them gently, replacing absolutes with gradients. We are not alone or unique in the way we once imagined. We are part of a distribution. That realization can be unsettling, but it can also be liberating. It suggests that life is not a miracle reserved for one planet, but a process embedded in the universe. If so, then meaning does not come from exclusivity. It comes from participation. There is another implication embedded in the 99.7% figure: responsibility. If life is likely elsewhere, then it may be fragile elsewhere as well. We know how easily ecosystems can collapse. We have seen how small changes can cascade into irreversible damage. Understanding life as common does not make it cheap. It makes it precious everywhere. The same probability frameworks used to infer life elsewhere are being applied closer to home. Climate models, biodiversity assessments, and epidemiological forecasts all rely on probabilistic reasoning. They do not predict the future. They outline possible futures and their likelihoods. Ignoring them does not make uncertainty disappear. It merely increases risk. In this sense, learning how scientists measure life beyond Earth can teach us how to think better about life on Earth. The 99.7% probability is also a reminder of scale. It reflects an extraordinary alignment of technology, theory, and patience. The data traveled light years. The instruments were calibrated to detect differences of parts per million. The analysis required supercomputers and decades of accumulated knowledge. This is not intuition. It is civilization-level cognition. And yet, the conclusion remains provisional, that humility is not weakness. It is strength. It allows science to advance without collapsing under its own claims. It keeps discovery open-ended, responsive, and self-correcting. As we refine our instruments and expand our models, probabilities will change. They may rise. They may fall. New explanations may emerge, but the process itself will endure. It is the method that matters as much as the result. The idea that life can be measured, not directly observed, challenges our intuitive understanding of reality. It forces us to accept that some truths are statistical, that knowledge can be strong without being absolute, that belief can be rational without being final. This is not just a scientific lesson, it is a philosophical one. We live in a universe where certainty is rare, but meaning is abundant, where probability guides action, and understanding deepens through iteration rather than revelation. The search for life beyond Earth is not a quest for comfort. It is a test of intellectual maturity. The 99.7% probability does not tell us who lives on that planet, what they look like, or how they think. It tells us something subtler and more important. The universe is capable of producing life more than once, and we are capable of recognizing the sign. That recognition changes the story of science from exploration to relationship. We are no longer simply observers of a lifeless cosmos. We are interpreters of a living one. And that, more than any single discovery, is what defines this moment. We have learned how to listen to the universe in its own language, not through myth or speculation, but through spectra, models, and probabilities. We have learned to ask better questions, accept nuanced answers, and remain open to revision. The number 99.7% is not a conclusion. It is an invitation to continue measuring, refining, and understanding, to accept uncertainty without fear, to embrace a universe that is richer, more complex, and more alive than we once believed. In learning how scientists measure life, we are also learning how to measure ourselves, how we think, how we reason, and how ready we are to inhabit a universe that no longer revolves around us, but includes us, one probability among many, in a cosmos still unfolding. 3. The chemistry of hope. Water, carbon, and alien atmospheres. Hope, in science, is not a feeling. It is a pattern. It is what emerges when order persists against chaos, when complexity appears where simplicity should reign, when chemistry begins to behave in ways that suggest intention without consciousness. In the search for life beyond Earth, hope does not arrive as a signal saying, "We are here." It arrives quietly, encoded in molecules, ratios, and reactions. It arrives in water, in carbon, and in atmospheres that refuse to remain inert. To understand why scientists speak of the chemistry of hope, we must first strip away romance and return to fundamentals. Life, at its core, is a chemical phenomenon. Before there were cells, before there were organisms, before there was evolution, there was chemistry capable of remembering itself. Atoms bonded, structures repeated, reactions fed reactions. Somewhere in that chain, matter crossed a threshold. It began to sustain patterns over time. Water plays a central role in this story, not because it is magical, but because it is uniquely suited to support complexity. Its molecular structure allows it to dissolve a vast range of substances, to transport energy efficiently, and to remain liquid across a wide range of temperatures. It is both stable and dynamic, a rare balance in a universe that favors extremes. Water cushions reactions, moderates environments, and enables the slow, intricate dance of chemistry that life requires. When scientists search for water on distant worlds, they are not searching for oceans alone, they are searching for possibility. Water vapor in an atmosphere suggests active cycles, evaporation, condensation, movement. Liquid water implies pressure and temperature conditions that allow chemistry to proceed gently, rather than violently. Ice, too, tells a story, preserving molecules and shielding them from radiation, offering stability over immense spans of time. But water alone is not enough. Carbon is the great architect of life, as we know it. Its ability to form 4 bonds allows it to create chains, rings, and complex 3-dimensional structures. No other element rivals its versatility. Carbon does not dictate what life must look like, but it allows for an almost limitless vocabulary of molecular forms, proteins, lipids, nucleic acids. These are not inevitable outcomes, but they are natural ones when carbon chemistry is allowed to explore its full potential. When carbon appears in an alien atmosphere, it is not surprising. Carbon is abundant in the universe. What matters is how it appears, in what forms, and in what relationships. Carbon dioxide alone is common. Methane alone can arise through non-biological processes. But when multiple carbon-bearing molecules coexist in patterns that resist equilibrium, the story changes. Atmospheres are not passive shells. They are dynamic systems shaped by geology, radiation, gravity, and, on at least one planet, life. An atmosphere remembers what happens on the surface below. Volcanoes leave signatures. Oceans exchange gases. Sunlight reshapes molecules, and life, if present, rewrites everything. On Earth, our atmosphere is profoundly unnatural. Oxygen should not dominate. Methane should not persist. Nitrous oxide should be fleeting, and yet they remain, replenished continuously by biological activity. Our sky is a chemical confession. Something here is alive. When the James Webb Space Telescope examines alien atmospheres, it is not searching for replicas of Earth. It is searching for confessional systems that reveal ongoing processes too complex, too persistent, to be easily explained by physics alone. The chemistry of hope lies in imbalance. in tension, in molecules that coexist only because something keeps them from settling down. Hope also lies in ratios. The proportion of gases matters as much as their presence. A trace amount of water vapor suggests transient conditions. Abundant water suggests stability. Carbon in isolation suggests potential. Carbon embedded in a network of reactive compounds suggests activity. These distinctions are subtle, but they are measurable and they matter. One of the most profound realizations in modern astrobiology is that life does not announce itself loudly. It whispers through chemistry. It nudges systems away from equilibrium and holds them there. It creates gradients of energy, of concentration, of structure. Where gradients persist, something is working. This is why atmospheres are such powerful tools. Unlike surfaces, which are difficult to resolve across light years, atmospheres interact directly with starlight. They are legible at a distance. They encode information in absorption lines and emission spectra, turning planets into readable texts. When scientists talk about alien atmospheres, they are not indulging in science fiction. They are reading chemical narratives written over millions of years. They are reconstructing climates, cycles, and possibilities. An atmosphere rich in water vapor but poor in carbon compounds tells one story. An atmosphere with carbon chemistry but little hydrogen tells another. Each combination narrows the range of explanation. Hope emerges when explanations converge on life, not as an assumption, but as a solution. There is a temptation to anthropomorphize this process, to imagine scientists searching the universe with yearning. The reality is more restrained, but no less profound. Scientists are cautious because nature is clever. It finds ways to surprise us. Non-biological processes can mimic life under certain conditions. Ultraviolet radiation can split molecules. Geological activity can produce gases. Exotic chemistry can unfold on worlds unlike our own. This is why the chemistry of hope is not about single markers. It is about systems. It is about coherence across multiple lines of evidence. Water that suggests stability, carbon that suggests complexity, atmospheric disequilibrium that suggests activity. Together they form a pattern that is difficult to ignore. And yet, hope does not mean certainty. It means plausibility grounded in physics. It means the universe is not hostile to life's ingredients. It means the raw materials of biology, hydrogen, oxygen, carbon, nitrogen, are not rare exceptions. They are common. They are forged in stars, scattered by supernovae, and assembled by gravity. Life, in this view, is not a rebellion against the universe. It is a continuation of its chemistry. This reframes our relationship with existence itself. We are not outsiders in a dead cosmos. We are expressions of a universe capable of organizing itself into thinking matter. Water flows, carbon bonds, energy moves, and somewhere in that flow, awareness arises. The chemistry of hope also forces us to confront the fragility of life. The same delicate balances that allow life to exist can be easily disrupted. Change the temperature slightly, alter the radiation environment, remove liquid water, break the carbon cycles, and the system collapses back into sterility. This fragility is not a weakness. It is a signature. Life occupies a narrow band of possibility, not because the universe is cruel, but because complexity requires precision. The fact that we are finding planets that appear to sit within this band suggests that precision is not unique. That realization carries ethical weight. If life is chemically favored under certain conditions, then planets capable of supporting life may be common. And if they are common, then the destruction of life anywhere is not trivial. It is the erasure of a rare and meaningful process, even if it occurs more than once. The chemistry of hope also reshapes our understanding of time. Chemical processes unfold slowly. Atmospheric signatures integrate millions of years of activity. The water detected today may have cycled for eons. The carbon imbalance may reflect evolutionary processes long gone. We are seeing not a moment, but a history. This deep time perspective humbles human urgency. Our civilizations rise and fall in thousands of years. Chemical cycles persist for billions. Life, once established, can be remarkably resilient, but only within its constraints. Outside them, it vanishes without drama. There is a quiet poetry in this. Hope is not loud, it is persistent. It survives not by force, but by balance. It adapts rather than conquers. The chemistry of hope does not dominate a planet. It integrates with it. As we interpret alien atmospheres, we are also learning how to read our own. Earth's atmospheric changes over the last 2 centuries are stark. Carbon dioxide rising, methane increasing, chemical balances shifting rapidly. From a distant telescope, our planet would appear suddenly unstable, not with the signature of emerging life, but with the signature of a technological species altering its environment. This is a sobering mirror. The same tools used to infer life elsewhere reveal vulnerability here. They remind us that atmospheres are responsive. They record behavior. They do not judge, but they do not forget. The chemistry of hope can become the chemistry of warning if balance is lost. In this sense, the search for alien life is also an exercise in self-awareness. It teaches us what signatures matter. It shows us what persistence looks like. It reveals how easily systems can tip. And yet, the overarching message remains hopeful. The universe is chemically generous. It provides the ingredients. It allows complexity. It does not require miracles. Water forms naturally. Carbon bonds eagerly. Energy flows everywhere. Given time, chemistry explores possibilities. And sometimes, those explorations stabilize into life. That does not guarantee intelligence. It does not guarantee longevity, but it guarantees opportunity. The planet identified by the James Webb Space Telescope represents such an opportunity made visible. Its atmosphere tells a story of interaction rather than stasis, of cycles rather than decay, of chemistry that refuses to simplify. That refusal is the seed of hope. Hope in this context is not about contact or colonization. It is about connection. It is about recognizing that the same laws shaping our existence operate elsewhere, that the story of matter organizing into meaning may be unfolding in parallel, unseen but not unimaginable. This realization can change how we think about ourselves. We are not anomalies, we are examples. Not the only outcome, but one expression among many. That does not make us less valuable. It makes us more responsible. Because if life arises from chemistry given time and care, then preserving those conditions here and elsewhere is an ethical imperative, not a sentimental one. The chemistry of hope teaches patience. It teaches restraint. It teaches respect for processes larger than ourselves. It reminds us that the universe is not empty of potential, even if it is quiet. As we continue to study water, carbon, and alien atmospheres, we are not just cataloging planets. We are mapping the conditions under which meaning can emerge. We are learning what the universe permits, what it resists, and what it quietly nurtures. Hope, then, is not something we project onto the stars. It is something we recognize in their chemistry. And in recognizing it, we take one step closer to understanding not just where life might exist, but why life exists at all. 4. Exoplanets and the cosmic lottery of existence. Every life that has ever existed is the result of a draw from an unimaginably vast lottery. Not a lottery with tickets and numbers, but one governed by physics, probability, and time. The universe does not choose winners with intention, yet outcomes emerge. Some are simple, some complex, and a very small number become aware enough to ask how they came to be. When we speak of exoplanets and the cosmic lottery of existence, we are not talking about luck in a human sense. We are talking about the intersection of inevitability and chance on a scale so large that intuition begins to fail. For most of human history, planets were rare in our imagination. They were confined to our solar system, a small family of worlds orbiting a single star. Earth felt singular not only because it hosted life, but because there seemed to be so few places where life could even try. The discovery of exoplanets shattered that illusion quietly, without spectacle, through data rather than drama. One star after another revealed companions, then hundreds, then thousands. Today we know that planets are not exceptions. They are the rule. Nearly every star hosts worlds. This realization alone reshapes the meaning of existence. If stars are common and planets are common around stars, then the stage for life is everywhere. The question is no longer whether there are enough theaters for the play to be performed, but how often the script reaches its most complex acts. The cosmic lottery begins with star formation. Stars differ in mass, temperature, lifespan, and stability. Some burn hot and fast, living brief, violent lives. Others glow steadily for trillions of years. A planet's fate is tied intimately to the nature of its star. Too much radiation, and atmospheres are stripped away. Too little energy and chemistry sullies into sterility. The star is the first roll of the dice. Then come planets themselves. They form from disks of gas and dust, chaotic environments shaped by collisions, migrations, and resonances. Worlds are thrown inward, flung outward, shattered, merged, and reshaped. Some end up scorched, others freeze. A few settle into regions where temperatures allow liquids to persist. These so-called habitable zones are not guarantees of life, but they are invitations. Yet even within a habitable zone, nothing is assured. A planet's mass determines whether it can hold an atmosphere. Too small, and gases escape into space. Too large, and crushing pressures may prevent stable surfaces. Its composition matters. Iron cores generate magnetic fields that shield atmospheres from stellar winds. Water must arrive in the right amounts, not so little that chemistry stalls, not so much that continents drown. Impacts can sterilize or seed. Tectonics can recycle nutrients or lock them away. Each factor is another draw. From a human perspective, this accumulation of requirements can feel overwhelming, as if life requires a miraculous alignment. But when the number of trials is vast enough, even rare outcomes become inevitable. This is the paradox at the heart of the cosmic lottery. Individual chances may be slim, but the universe buys an enormous number of tickets. Exoplanets reveal just how many tickets are in play. We have found worlds larger than Jupiter orbiting in days, defying earlier models. We have found rocky planets hugging their stars, and others drifting alone through interstellar space. We have found systems with 7 planets locked in gravitational harmony, and systems in violent instability. Diversity is not the exception. It is the baseline. Within this diversity, life's requirements are not single points but ranges. There is not one perfect Earth-like scenario, but many possible pathways. Life adapts to conditions. It exploits gradients. It colonizes niche. On Earth, life thrives in boiling vents, frozen ice, acidic pools, and deep underground. This adaptability widens the lottery's acceptable outcome. What matters most is not perfection, but persistence. Time is the most underrated variable in the cosmic lottery. The universe is patient beyond comprehension. Given millions of years, chemistry explores countless configurations. Given billions, it explores nearly all of them. Reactions fail, collapse, restart. Structures form, break, reform. Most pathways lead nowhere. A few stabilize, and stabilization, once achieved, can compound. Life does not need to arise quickly. It only needs to arise once and then survive long enough to diversify. Exoplanets that appear old and stable become especially compelling. They represent worlds where the lottery has been running for a long time, where chance has had repeated opportunities to settle into structure, where early failures may have been followed by later successes. This perspective dissolves the idea that Earth's history was uniquely blessed. Instead, it suggests that Earth was one of many worlds where the numbers eventually came up favorable, not chosen, not special in intention, but special in outcome. This does not diminish the wonder of our existence. It reframes it. The cosmic lottery also extends beyond biology into consciousness. Simple life may be common. complex life less so, intelligent, technological life rarer still. Each transition adds constraints. Each constraint narrows probability. Multicellular organization requires cooperation. Intelligence requires energy-intensive brains. Technology requires environmental stability and accessible resources. Each step is another The silence of the cosmos may reflect this narrowing funnel. Many worlds may host life. Fewer may host animals. Fewer still may host civilizations capable of altering their planets or signaling across space. The lottery may pay out at early stages frequently, but jackpot winners are rare. This rarity has implications for how we view ourselves. We are not the expected outcome of evolution. We are one possible outcome among many. Intelligence is not guaranteed. It is contingent. It arises when pressures favor foresight, social coordination, and abstraction. Those pressures may not exist everywhere, or may not persist long enough. Understanding this fosters humility. It suggests that our cognitive abilities are not destiny's crown, but a fragile experiment. One that can fail. Exoplanets also reveal something subtle about existence itself. Most worlds are inhospitable. The universe is not designed for comfort. It is dominated by vacuum, radiation, and extremes. Life exists not because conditions are generally friendly, but because life exploits rare pockets of stability. This is the deeper meaning of the lottery metaphor. The universe does not favor life, but it permits it. It does not optimize for consciousness, but it allows it to emerge. And once it does, that consciousness can reflect on the odds that brought it into being. From that reflection arises gratitude, not in a spiritual sense necessarily, but in an existential one. To exist at all is to have passed through filters so numerous that their product feels miraculous, even if it is natural. Exoplanet science also forces us to reconsider the notion of normal. Earth feels normal to us because we evolved here, but from a cosmic perspective, Earth may be unusual in some ways and ordinary in others. Its oceans, continents, plate tectonics, and biosphere represent one configuration among many. Other worlds may host life under conditions that feel alien but are no less valid. This challenges the subtle anthropocentrism that often sneaks into discussions of habitability. The cosmic lottery does not draw human-shaped winners. It draws whatever fits the rules of chemistry and physics. Life elsewhere may be microbial, slow, resilient, and utterly indifferent to the questions that consume us. And yet, the fact that we can ask these questions at all is part of the same lottery. The emergence of a species capable of detecting exoplanets, analyzing spectra, and inferring probabilities is itself an improbable outcome. It required not only biology, but culture, language, mathematics, and cooperation across generations. It required societies stable enough to invest in telescopes that would not return immediate benefits. It required curiosity that survived despite no guarantee of answer. In this sense, the cosmic lottery does not end with life. It continues through knowledge. Exoplanets are not just objects of study. They are mirrors reflecting the contingency of our own existence. Each newly discovered world is a reminder that Earth could have been different. Slight changes in orbit, composition, or timing could have rendered it barren. We are not standing on inevitability. We are standing on improbability made real. This awareness carries ethical weight. If existence is the outcome of a lottery we did not control, then preserving it is not optional. It is stewardship of something rare, even if it is not unique. The fact that life may exist elsewhere does not cheapen life here. It heightens its value by placing it within a larger pattern that is still precious at every occurrence. The cosmic lottery also reshapes the meaning of progress. Human history often frames progress as destiny, as if technological advancement were inevitable. Exoplanet science suggests otherwise. Many worlds may host life that never develops technology. Many civilizations may arise and disappear without leaving lasting traces. Progress is not guaranteed. It is conditional. This realization reframes our moment in history. We are a civilization with the ability to understand its cosmic context. And with that understanding comes choice. We can act as if survival and knowledge are automatic, or we can recognize them as fragile achievements. The lottery metaphor reminds us that while we did not choose the initial draw, we influenced the subsequent ones. Our actions shape whether intelligence persists or collapses, whether our planet remains habitable or becomes another cautionary tale written into its atmosphere. Exoplanets also expand the temporal horizon of hope. Even if intelligent life is rare now, the universe is young relative to its future. Many stars have not yet reached stable phases conducive to life. Many planets have not yet cooled. The lottery will continue to run long after humanity's current form has changed or vanished. This perspective loosens the grip of immediacy. It suggests that life's story is not confined to our era, that existence is an ongoing experiment, with many chapters yet unwritten. And yet, we are here now. We are the beneficiaries of an unbroken chain of favorable outcomes stretching back to the first moments of the universe. We are the result of stars that formed heavy elements, planets that retained atmospheres, chemistry that crossed thresholds, and evolution that favored cognition. The cosmic lottery did not guarantee us, it produced us. Exoplanets teach us that we are not alone in possibility, even if we are alone in experience for now. They show us that existence is neither trivial nor destined. It is contingent, conditional, and therefore meaningful. To exist is to have won, not against others, but against non-existence itself. This understanding can change how we live. It can foster humility instead of dominance, curiosity instead of fear, and responsibility instead of entitlement. If life is a rare pattern emerging from vast randomness, then sustaining it is not just a biological imperative, but a cosmic one. The cosmic lottery of existence does not promise fairness, it does not reward virtue, it does not guarantee continuation. But it offers something profound, the chance for matter to become aware, for the universe to look back on itself through conscious eyes. Exoplanets tell us that this chance is not confined to one place, that awareness may flicker on in many corners of the galaxy, separated by distance but united by physics. Each instance is independent, yet part of the same story. We do not know how many times the lottery is already paid out. We do not know how many winners have come and gone in silence. But we know this. The universe is capable of producing life, and it is capable of producing minds that wonder about it. That knowledge alone changes everything. The cosmic lottery is not about odds. It is about perspective. It teaches us that existence is neither meaningless nor guaranteed. It is possible, and possibility, once realized, carries responsibility. Among countless exoplanets, one gave rise to us. Among countless outcomes, we are here, not because the universe needed us, but because it allowed us. And now that we know how wide the lottery truly is, the question is no longer whether life is rare, but whether we are wise enough to value it wherever it appears. Point 5. From starlight to data. How James Webb sees the invisible. Every discovery made by the James Webb Space Telescope begins not with images, but with patience. Before there are spectra, before there are probabilities, before there are headlines, there is starlight, ancient, fragile, and unimaginably faint. That light has traveled across space for years, centuries, sometimes billions of years, carrying information encoded not in language, but in wavelength. The achievement of James Webb is not that it sees farther than any telescope before it, but that it understands what it sees. To grasp how Webb reveals the invisible, we must first confront a simple truth. Most of the universe cannot be seen with human eyes. The cosmos is not dominated by light in the narrow band we evolved to perceive. It is filled with infrared radiation, with heat signatures, molecular vibrations, and subtle shifts in energy that pass unnoticed by our biology. Our eyes are tuned for survival on one planet, under one star. James Webb is tuned for reality. Infrared light is older than visible light. As the universe expands, light stretches, shifting toward longer wavelengths. What was once bright and energetic becomes faint and red. The earliest galaxies, the cold dust clouds where stars are born, and the atmospheres of distant planets all speak most clearly in infrared. Previous telescopes could hear whispers. Webb can hear conversation, but hearing is not seeing. Webb does not simply capture light, it dissects it. Every photon that reaches the telescope is a data point. Its energy, timing, and direction are recorded, sorted, and interpreted. This process transforms starlight into information, and information into understanding. The journey begins when a distant star emits light. If a planet passes in front of that star from our perspective, a tiny fraction of the light passes through the planet's atmosphere before reaching Webb. During that brief transit, atmospheric molecules of specific wavelengths, the light arrives slightly dimmer at those wavelengths, carrying the imprint of what it encountered along the way. This dimming is almost imperceptible. We are talking about changes measured in parts per million. Detecting them requires extraordinary stability, precision, and calibration. James Webb was designed for this exact challenge. Its mirror, composed of 18 gold-coated segments, acts as a single enormous collector of faint signals. Gold is not chosen for luxury, but for physics. It reflects infrared light with exceptional efficiency. Yet, collecting light is only the first step. The real work happens after the photons are captured. Webb's instruments split incoming light into its component wavelengths, producing spectrographs that show how much light arrives at each energy level. These spectra are the fingerprints of atoms and molecules: hydrogen, oxygen, carbon, nitrogen, methane, water vapor. Each leaves a distinct pattern. These patterns are not ambiguous. They are the result of quantum mechanics, governed by laws that hold everywhere in the universe. This is where the invisible becomes legible. To the untrained eye, a spectrum may look like a series of dips and peaks. To a scientist, it is a story. A dip here suggests absorption by water vapor. Another suggests carbon dioxide. A subtle slope reveals temperature gradients. A missing feature rules out certain chemical processes. Over time, as data accumulates, uncertainty shrinks. What makes James Webb revolutionary is not just sensitivity, but integration. Its instruments work together, cross-checking results, observing the same target in different ways, at different wavelengths, under different conditions. This redundancy is not wasteful. It is essential. It allows scientists to distinguish real signals from noise, patterns from artifacts. Noise is the enemy of discovery. Every telescope must contend with it. Thermal fluctuations, cosmic rays, instrumental drift, all can masquerade as signals if not carefully accounted for. Webb minimizes these effects through design and placement. Orbiting far from Earth, shielded by a sunshade the size of a tennis court, it remains extraordinarily cold. Cold instruments produce less infrared noise, allowing faint cosmic signals to stand out. This cold, quiet environment turns Webb into a listening device for the universe. It does not shout, it waits. From this waiting emerges data of unprecedented clarity. But clarity does not equal simplicity. Raw data is messy. It must be processed, cleaned, and interpreted. This is where human ingenuity meets machine precision. Teams of scientists analyze Webb's output using models built over decades. They simulate planetary atmospheres under countless conditions, adjusting variables and comparing predicted spectra with observed ones. This is not pattern matching by intuition. It is statistical inference, grounded in physics and refined through iteration. Each analysis asks the same question in different ways. What combination of conditions best explains what we see? Sometimes the answer is mundane: a hot gas giant with clouds of silicates, a barren rock scorched by its star. But sometimes the answer resists simplicity. Certain combinations of gases appear together when they should not. Certain temperatures persist when they should fluctuate. Certain features recur across observations. This is where invisibility becomes insight. James Webb does not confirm life directly. It does not see organisms. It sees environments. It reveals whether a planet has an atmosphere at all, whether that atmosphere is stable, whether it contains molecules associated with chemistry that on Earth is inseparable from biology. It shows us not the actors, but the stage. This distinction matters. It keeps science honest. It prevents premature conclusions. It also makes the discovery process more profound. We are not witnessing a spectacle. We are uncovering a system. There is something deeply human about this approach. We have always learned by inference. We read footprints, not the animal itself. We reconstruct history from ruins. We diagnose illness from symptoms. Webb extends this habit beyond Earth, applying it to entire worlds. The transformation from starlight to data is also a transformation from wonder to responsibility. With each improvement in measurement, the universe becomes less abstract. It becomes a place with conditions, histories, and trajectories. Worlds stop being points of light and start being environments. This shift has philosophical consequences. When planets become environments, the question of life becomes practical rather than speculative. We begin to ask, not, could life exist, but what would sustain it? Not, are we alone, but how common are conditions like ours? James Webb also teaches us humility in the face of complexity. The data it provides often raises as many questions as it answers. Unexpected features appear. Models must be revised. Assumptions are challenged. This is not failure. It is progress. The invisible resists easy interpretation because the universe is richer than our first approximations. Yet, despite this complexity, the underlying process remains elegant. Light interacts with matter. Matter follows laws. Laws produce patterns. Patterns can be measured. Measurement leads to understanding. This chain links distant stars to human minds. Consider what it means that we can detect the atmospheric composition of a planet hundreds of light years away. The photons carrying that information left their source before modern science existed. They traveled through expanding space, unaffected by the rise and fall of civilizations, and now they end their journey inside detectors built by a species that evolved from primates on a small planet orbiting an ordinary star. This is not just technology, it is continuity. James Webb embodies the idea that knowledge is cumulative. It builds on the work of Newton and Maxwell, of Planck and Einstein, of astronomers who mapped the skies long before we could see beyond visible light. Every equation encoded in Webb's software represents centuries of collective effort. From starlight to data, then, is not a single transformation. It is a chain of transformations across time, from physical laws to engineering, from engineering to observation, from observation to interpretation, from interpretation to meaning. And meaning is where the invisible becomes personal. When Webb reveals water vapor in an alien atmosphere, it is not just confirming a molecule, it is revealing a possibility. When it detects carbon chemistry, it is not just counting atoms, it is mapping pathways. When it measures disequilibrium, it is not just noting imbalance, it is hinting at activity. This does not mean we should rush to conclusions, but it does mean we are no longer blind. For most of history, the universe was a silent backdrop. Stars were lights, planets were wanderers. Meaning was projected, not inferred. James Webb marks a transition from projection to detection. We are no longer guessing blindly. We are reading requires literacy, and Webb has given us a new alphabet. Infrared spectra are that alphabet. Each line, each curve, each anomaly is a letter. Combined, they form words about temperature, composition, and dynamics. Over time, as we observe more worlds, we begin to recognize grammar, patterns repeat. Exceptions stand out. The universe becomes legible. This legibility changes our relationship with space. It becomes less mythic and more intimate, not in the sense of familiarity, but in the sense of connection. The same physics shaping distant atmospheres shapes our own. The same molecules absorb light there and here. The same rules apply. This continuity is profoundly grounding. It reminds us that we are not outsiders peering into an alien realm. We are participants in the same physical story. James Webb also reveals the limits of vision. There are things it cannot see. It cannot detect small planets around certain stars. It cannot resolve surfaces. It cannot confirm biology directly. Acknowledging these limits is part of its strength. It defines the boundary between evidence and imagination. Yet even within those boundaries, the telescope has expanded what counts as evidence. It has made the invisible measurable. It has turned faint differences into decisive data. It has shown that absence of visible light does not mean absence of information. This lesson extends beyond astronomy. It speaks to how we understand reality itself. Much of what matters is not immediately visible. Systems operate beneath the surface. Patterns emerge only with patience and precision. James Webb is a reminder that insight often requires tools that transcend intuition. There is also a cultural significance to this way of seeing. In an era dominated by immediacy and spectacle, Webb represents a different tempo. It does not produce constant images, it produces deep ones. It rewards waiting, it values accuracy over speed. This ethos is quietly radical. From starlight to data, Webb transforms distance into relevance. A planet hundreds of light years away becomes a subject of serious inquiry. Its atmosphere is analyzed, its history inferred, its potential discussed. Distance no longer equals ignorance, and yet distance still matters. These worlds remain unreachable in any practical sense. This creates a unique tension. We can know, but not touch. We can infer, but not intervene. Knowledge without control is a rare state for humanity, and a healthy one. It forces restraint, it encourages respect, it keeps wonder alive. James Webb does not answer the question of life alone, but it reframes it in a way that makes future answers possible. It shows that the invisible is not unknowable. It shows that with the right tools, patience, and humility, the universe can be read rather than imagined. From starlight to data is the story of how we learn to listen without expecting a reply, how we learn to measure without dominating, how we learn to let the universe speak in its own language. And in doing so, we discovered that the invisible is not empty. It is rich with structure, history, and possibility, waiting not to be seen, but to be understood. 6. The quiet question: what do we mean by life? Before we can ask whether life exists elsewhere in the universe, we have to confront a quieter, more difficult question. What do we actually mean by life? This question sounds simple, almost childish, until we try to answer it with precision. The moment we do, certainty dissolves, definitions fracture, assumptions reveal themselves, and we realize that life, the thing we are so eager to find, is far stranger and more subtle than we often admit. On Earth, life feels obvious. It moves, grows, reproduces, adapts. It breathes, consumes, competes. We recognize it instinctively because we are immersed in it. We are it, but that familiarity can be deceptive. It encourages us to mistake examples for definitions and experiences for principles. When scientists search for life beyond Earth, they cannot rely on intuition. They need criteria that work in places we have never been, under conditions we have never experienced. This is where the quiet question begins. At its most basic level, life is often described as a system capable of metabolism, growth, reproduction, and evolution. This definition works reasonably well for most organisms we know, but it fails at the edges. Viruses reproduce and evolve, but only inside hosts. Are they alive? Prions replicate without DNA or RNA. Are they alive? Fire consumes energy, grows, spreads, and responds to its environment. Is it alive? The more we probe, the more the boundaries blur. This ambiguity is not a failure of biology. It is a reflection of reality. Life is not a binary state. It is a spectrum of organization. Somewhere along that spectrum, chemistry becomes biology, and biology becomes consciousness. The transitions are gradual, not abrupt. For the purposes of astrobiology, this spectrum matters enormously. We are not looking for animals or plants. We are looking for systems that occupy a particular region of this continuum, systems that maintain themselves far from equilibrium by processing energy and information. Life, in this sense, is not defined by what it looks like, but by what it does. It takes matter and makes it persistent. The universe left alone trends toward disorder. Energy spreads, structures decay, complexity erodes. Life is remarkable because it locally reverses this trend. It creates islands of order by exporting entropy to its surroundings. It builds structures that last, not forever, but long enough to matter. This capacity to resist equilibrium is one of the most powerful ways to think about life. From this perspective, life is not a thing but a process. This process requires three ingredients: a source of energy, a medium for complex chemistry, and a way to store and transmit information. On Earth, energy comes primarily from the sun. Chemistry unfolds in water, and information is stored in DNA. But these specifics may not be universal. What matters are the functions, not the forms. Energy can come from many sources. Sunlight is only one option. Chemical gradients, geothermal heat, radioactive decay, all can drive metabolism. On Earth, entire ecosystems thrive in darkness around hydrothermal vents, sustained by chemical energy alone. This teaches us an important lesson. Life does not require sunlight. It requires disequilibrium. The medium for chemistry also need not be water, though water is exceptionally good at the job. Other solvents, like ammonia or methane, could in principle support alternative chemistries under different temperatures and pressures. These possibilities stretch our imagination, but they remain grounded in physics. The universe does not privilege water. It simply allows information storage is perhaps the most profound requirement. Life must remember itself. It must encode instructions for building and maintaining structure, and those instructions must be transmissible with variation. On Earth, this role is played by nucleic acids. Elsewhere, the substrate could differ, but the need for information does not. Without memory, there is no evolution. Without evolution, there is no accumulation of complexity. Without complexity, life cannot escape the tyranny of simplicity. When scientists talk about detecting life through atmospheric signatures, they are not claiming to see organisms, they are claiming to see the consequences of this process. They are looking for evidence that a planet's chemistry is being driven persistently away from equilibrium in a way that suggests ongoing information-guided activity. This is a subtle but critical distinction. We are not asking, is there something alive there right now? We are asking, is there a system there that behaves the way life behaves? This shift in emphasis allows us to search broadly without being constrained by Earth-centric expectations. It also forces humility. We must accept that alien life, if it exists, may not resemble anything we know. It may not be cellular. It may not be fast. It may not be obvious. It may operate on timescales that make our own feel frantic. It may be microbial and remain so forever. Or it may have passed through complexity and collapsed long before its light reached us. This uncertainty is not discouraging. It is intellectually honest. The quiet question of life also exposes a philosophical tension. We often want life to be special, meaningful, and rare. At the same time, we want it to be discoverable, understandable, and governed by laws. These desires pull in opposite directions. If life is too special, it becomes miraculous and unknowable. If it is too common, it risks feeling mundane. Science navigates this tension by refusing both extremes. Life is neither a miracle nor a triviality. It is an emergent phenomenon, a natural outcome under certain conditions, and a rare one in the broader context of the universe. Emergence is key here. Life is not written into the laws of physics explicitly. There is no equation that says at this point life appears. Instead, life emerges when systems become complex enough for new properties to arise. Wetness emerges from water molecules even though no single molecule is wet. Consciousness emerges from neural networks even though no single neuron is conscious. Life emerges from chemistry. This means that life is both lawful and unpredictable. It follows rules, but it is not reducible to them in any simple way. This duality explains why defining life is so difficult. We are trying to capture an emergent process with static criteria. When we ask whether a distant planet has life, we are really asking whether that planet has crossed a threshold of complexity, whether chemistry there has begun to behave historically rather than repetitively, whether the past influences the future in a way that allows adaptation. History is a crucial marker of life. Non-living systems can be complex, but they do not remember. A crystal grows according to fixed rules. A hurricane forms and dissipates. These systems do not accumulate changes that alter their fundamental behavior over generations. Life does. Life learns, not consciously at first, but structurally. It becomes shaped by what has worked before. This historical dimension is what makes life fragile and resilient at the same time. Fragile because it depends on continuity. Resilient because it can adapt. When scientists infer life from atmospheric data, they are inferring history. They are inferring that whatever is shaping that atmosphere has been doing so for long enough to leave a persistent mark. They are seeing not a snapshot, but a trajectory. This brings us to an uncomfortable realization. Life does not require intelligence. It does not require awareness. It does not require meaning. These are later developments, contingent and rare. Most life in the universe, if it exists, is likely simple, and that is not a disappointment. It is a reminder of how much work complexity requires. Human intelligence sits at the extreme end of the life spectrum. It is energy-intensive, fragile, and dependent on stable environments. It may be one of the rarest outcomes of the cosmic process, but it is not the definition of life. It is one possible expression. Understanding this can recalibrate our expectations. The discovery of microbial life elsewhere would not be a failure. It would be a confirmation that the universe knows how to build living systems at all. That alone would be transformative. The quiet question also has ethical implications. How we define life determines how we value it. If life is rare and precious, it demands protection. If life is common, it still demands respect, because each instance represents a unique history of emergence. If we find evidence of life elsewhere, even simple life, it will challenge us to think beyond human-centered ethics. It will force us to consider whether life has intrinsic value, independent of intelligence or utility. These questions are not academic. They will shape future exploration, policy, and responsibility. The question of life also reflects back on Earth in unexpected ways. As we refine our criteria for life elsewhere, we sharpen our understanding of life here. We see our biosphere not as a static backdrop, but as a dynamic system maintained by countless interacting processes. We recognize how easily those processes can be disrupted. Climate change, biodiversity loss, and ecosystem collapse are not just environmental issues, they are threats to the very process that defines life as we know it. The same atmospheric signatures we look for on distant planets are being altered here by us. This parallel is not accidental. It is a consequence of understanding life as a planetary phenomenon. Earth's life does not exist in isolation from its atmosphere, oceans, and geology. It shapes them and is shaped by them. Life is not on the planet. It is part of the planet. This insight is essential when thinking about alien worlds. If life exists elsewhere, it will be woven into its planet's systems, not separate from them. The quiet question also invites existential reflection. If life is a process that emerges naturally under certain conditions, then meaning does not come from being unique. It comes from being part of something larger. We are expressions of a universe capable of complexity, not anomalies defying it. This does not strip life of significance. It deepens it. To be alive is to participate in a long chain of emergence stretching back to the earliest moments of the cosmos. It is to be matter that remembers, adapts, and persists. It is to be part of a story that the universe tells through chemistry and time. When we ask what we mean by life, we are also asking what we mean by ourselves. Are we accidents or outcomes? Are we separate from nature or continuous with it? Are we observers of the universe or expressions of it? Science does not answer these questions definitively, but it reframes them. It moves them from the realm of mystery to the realm of inquiry. The James Webb Space Telescope does not define life. It gives us the tools to recognize its signatures. It allows us to ask the quiet question with greater clarity and less projection. It forces us to confront our assumptions and refine our language, and in doing so, it reminds us that life is not something we own or fully understand. It is something we are still learning to describe. Perhaps the most profound implication of the quiet question is this: life may not be a category we discover, but a concept we continuously refine as we encounter new forms, new processes, and new possibilities. Our definition will evolve. This is not a weakness of science. It is its strength. To define life too narrowly would be to miss it when it appears in unfamiliar forms. To define it too broadly would be to dilute its meaning. The challenge is to define it just well enough to recognize it without assuming too much. That balance is what makes the search for life both rigorous and humbling. As we look out into the universe and interpret faint signals from distant worlds, we are engaged in a dialogue not with aliens but with reality itself. We are asking quietly and carefully whether the process that produced us has occurred elsewhere, and the universe, through chemistry and light, is beginning to answer, not loudly, not clearly, but enough to suggest that life is not a solitary phenomenon. In asking what we mean by life, we are not just preparing to find it elsewhere. We are preparing to understand it more deeply here. That is the power of the quiet question. 7. Habitable zones and the fragility of survival. When people hear the phrase habitable zone, it often sounds reassuring, even comforting. It suggests a place where life can simply exist, as if habitability were a stable condition rather than a delicate negotiation. But in reality, habitable zones are not guarantees of survival. They are narrow windows of possibility, defined not by abundance, but by balance. And balance, in the universe, is always fragile. A habitable zone is often described as the region around a star where temperatures allow liquid water to exist on a planet's surface. This definition is useful, but it is also incomplete. Liquid water is not life, and the presence of water does not ensure longevity. The habitable zone is not a sanctuary. It is a testing ground. To understand why survival is so fragile, even in the right place, we have to appreciate how many forces are acting simultaneously on any living world. Gravity pulls inward. Radiation bombards from above. Geology reshapes the surface from below. Chemistry reacts continuously. And time, the most relentless force of all, magnifies every instability. Earth sits within the sun's habitable zone, but even here, survival has never been guaranteed. Our planet has endured global ice ages, asteroid impacts, massive volcanic eruptions, and periods when oxygen itself was a poison to most existing life. Life survived not because conditions were easy, but because adaptation found ways to persist through catastrophe. The habitable zone, then, is not a promise of comfort. It is a range within which struggle can occur without immediate annihilation. Around other stars, this struggle takes on different forms. Stars vary enormously. Some are stable and long-lived, burning steadily for tens of billions of years. Others flare violently, unleashing radiation that can strip atmospheres and sterilize surfaces. A planet may orbit within the habitable zone in terms of temperature, yet still be rendered lifeless by stellar behavior alone. Red dwarf stars, for example, are the most common stars in the galaxy. Their habitable zones lie very close to the star, increasing the likelihood of tidal locking, where one side of the planet always faces the star, while the other remains in permanent darkness. This creates extreme climates, scorching heat on one hemisphere, deep freeze on the other. Life may still find niches, but the margin for error narrows. Stellar flares from such stars can be devastating. Bursts of radiation can erode atmospheres over time, especially if a planet lacks a strong magnetic field. Without that invisible shield, Charged particles from the star can slowly peel away the gases that make liquid water and stable climates possible. A planet can begin in the habitable zone and drift out of habitability without ever moving an inch. This highlights a crucial truth. Habitability is not just about distance. It is about protection. Magnetic fields, generated by molten planetary cores, play a vital role in survival. They deflect stellar winds and cosmic radiation, preserving atmospheres over geological timescales. Earth's magnetic field has waxed and waned, even flipped polarity many times. Yet it has persisted long enough to protect life. Without it, our planet might resemble Mars, a world that once had rivers and lakes, now stripped to a thin, cold shell. Mars is a cautionary tale written in rust-red stone. It likely began within the Sun's habitable zone, with liquid water on its surface and a thicker atmosphere, but its smaller size meant a weaker gravity and a cooling core. Its magnetic field faded. The solar wind took over. Over time, Mars lost the ability to support surface life, not because it was in the wrong place, but because it could not hold on. Venus tells a different but equally sobering story, similar in size to Earth and also within the broader habitable zone. Venus followed a divergent path. A runaway greenhouse effect trapped heat, evaporated oceans, and turned the planet into a furnace. Venus did not lose habitability through cold or atmospheric loss, but through excess. Too much of the same processes that sustain life on Earth became destructive. Together, Mars and Venus frame Earth's fragile success. They show us that being in the habitable zone is necessary, but not sufficient. Survival depends on long-term stability across many interacting systems. This fragility becomes even more pronounced when we consider time. Stars evolve. Their luminosity changes. Habitable zones move outward as stars age and brighten. A planet comfortably habitable for 1 billion years may eventually overheat. Another may thaw too late, after its atmosphere has already been lost. Timing matters as much as location. Life must not only arise, but arise early enough, and then persist long enough to adapt as conditions shift. This is an extraordinary demand. It requires resilience across epochs, not just moments. When we detect an exoplanet in the habitable zone, we are seeing a snapshot in an ongoing story. That planet may be entering habitability, leaving it, or hovering on the edge. The question is not just whether life could exist there, but whether it has had time to establish itself and survive the planet's changing conditions. This temporal fragility introduces a sobering perspective. The universe is vast, but the windows for survival may be brief. Worlds may flicker into habitability and then fade. Life may arise often, but endure rarely. On Earth, survival has depended on feedback loops that stabilize climate over long timescales. The carbon cycle, driven by weathering, volcanism, and biological activity, has acted as a planetary thermostat. When temperatures rise, carbon dioxide is drawn down. When temperatures fall, volcanic emissions accumulate, warming the planet. This balance is not perfect, but it has kept Earth within habitable bounds for billions of years. Such feedback systems are not guaranteed elsewhere. They require active geology and complex interactions between surface, atmosphere, and interior. A planet without plate tectonics may struggle to regulate its climate. One without oceans may lack the buffering capacity to absorb shocks. Each missing piece increases fragility. Even with all systems in place, survival remains precarious. Random events, asteroid impacts, nearby supernovae, gamma-ray bursts can reset the evolutionary clock or end it entirely. The universe does not shield life from chance, it exposes it to it. This reality reframes the idea of the Goldilocks zone. Conditions are not just right, they are just survivable. And survivability is a moving target. For a science-loving audience, this insight is both humbling and empowering. It humbles us by showing how narrow the margins truly are. It empowers us by revealing that life's persistence on Earth is not accidental, but the result of continuous balance and adaptation. The fragility of survival also changes how we think about intelligence. Intelligent life requires long periods of environmental stability. Complex organisms take time to evolve. Brains take energy. Societies require predictability. If habitable conditions fluctuate too wildly or end too soon, intelligence may never emerge, even if life itself does. This suggests that the universe may be full of worlds where life began but never reached complexity. Worlds that hosted microbial ecosystems for hundreds of millions of years before freezing, overheating, or losing their atmospheres. The cosmic silence we observe may not be evidence of emptiness, but of fragility. Understanding this can shift how we interpret discoveries like a planet with a high probability of life. Such a planet is not just exciting because life may exist there. It is exciting because it may represent a rare alignment of stability across time. It may be a world that has survived long enough to build something enduring, and yet fragility never disappears. Even on Earth, with all its resilience, survival is not guaranteed. Human activity is altering atmospheric chemistry at a pace rarely seen in geological history. We are pushing feedback systems toward limits they have not encountered before. From a distant telescope, Earth's habitability would appear increasingly stressed. This is not a coincidence. The same factors that make survival possible also make it vulnerable to disruption. A stable atmosphere can be destabilized. A balanced climate can be tipped. Fragility is not a flaw in the system. It is the price of complexity.
The habitable zone concept, then, should not inspire complacency. It should inspire care.
When we look for life elsewhere, we are also learning how easy it is to lose. We are learning that survival is not a static condition, but a dynamic achievement. It must be maintained, protected, and respected. This realization carries a quiet moral weight. If life is fragile everywhere, then preserving it where we find it becomes a universal responsibility, not because life is rare in principle, but because it is always at risk in practice. The fragility of survival also deepens the meaning of hope. Hope is not the assumption that things will work out. It is the commitment to sustaining balance, despite uncertainty. It is the willingness to invest in long-term stability, even when short-term gains tempt disruption. Earth's history shows that life can recover from catastrophe, but recovery takes time, often millions of years. Human timescales are shorter. Our decisions matter because they operate within a window that cannot be easily reset. The habitable zone is not a finish line. It is a beginning. It marks where survival is possible, not where it is assured. Life must still navigate countless challenges, many of them invisible until they become existential. In this sense, the search for habitable exoplanets is not just an astronomical endeavor, it is a philosophical one. It forces us to confront the reality that existence is conditional, that being here now is the outcome of sustained balance across deep time. We are not standing on solid ground. We are balancing on a narrow ridge between extremes, held there by feedback loops. We are only beginning to understand. This awareness can change how we think about progress. True progress is not endless growth or domination of environment. It is the ability to remain within survivable bounds. It is the discipline to recognize limits before they are crossed. The universe does not reward excess. It permits survival within constraints. Habitable zones are the spatial expression of that truth. Fragility is its temporal expression. When James Webb identifies planets within habitable zones, it is not pointing to havens. It is pointing to arenas, places where chemistry, physics, and time have aligned just enough to allow the possibility of endurance. Whether that possibility becomes reality depends on countless factors, many of them unpredictable. That uncertainty is not a reason for despair. It is a reason for reverence. To survive is not trivial. It is an ongoing accomplishment, renewed every moment. On Earth, survival has required cooperation between systems: atmospheric, biological, geological. It has required restraint as much as innovation. If life exists elsewhere, it will face the same challenge, not just to begin, but to continue. The fragility of survival is what makes it meaningful. If life were inevitable and indestructible, it would carry no weight. Its value emerges from its vulnerability. Habitable zones show us where life might stand a chance. Fragility reminds us that chance must be protected. In recognizing both, we gain a deeper appreciation of our place in the universe, not as guaranteed heirs of existence, but as careful stewards of a narrow, precious possibility. 80 Alien Skies, imagining a living world beyond Earth. When we imagine life beyond Earth, our first instinct is often to picture the beings themselves, their shapes, their intelligence, their technology. But before any creature walks, swims, or thinks, there is a sky. A living world announces itself first through its atmosphere, through the light filtered by alien clouds, through colors no human eye has ever seen rising over landscapes shaped by unfamiliar physics. To imagine alien life honestly, we must begin by standing beneath alien sky. Every sky tells a story. Earth's sky, blue by day and dark by night, is not just scenery. It is a consequence of our planet's gravity, chemistry, and history. The scattering of sunlight by nitrogen and oxygen, the gentle modulation of climate by water vapor, the protective shield of ozone. Our sky is both witness and participant in life's long survival. On another world, the sky would tell a different story, shaped by a different balance of forces, yet still bound by the same universal laws. Picture a planet orbiting a red dwarf star, where the sun never truly rises or sets. Instead, it hangs motionless in the sky, casting a permanent twilight across the surface. The sky here might glow deep orange or crimson, tinted by the star's cooler light. Clouds could be thick with hydrocarbons or water droplets shaped by lower gravity. Shadows would stretch endlessly in one direction. On such a world, life would evolve not to a rhythm of days, but to a rhythm of constancy. Biological clocks would be written differently. Sleep, growth, and behavior would be governed by chemistry rather than sunrise. Now, imagine a sky beneath which life thrives, not in oceans of water, but in lakes of methane and ethane, like those on Saturn's moon, Titan. The sky would be hazy, perpetually veiled by organic smog produced by photochemical reactions high in the atmosphere. Sunlight would arrive muted and amber, barely warming the surface. Rain would fall, not as water, but as liquid hydrocarbons. Life, if it exists there, would be slow, deliberate, operating at temperatures where Earth's biochemistry would freeze. And yet, survival would still be possible, achieved through pathways we are only beginning to imagine. Alien skies are not limited to gentle or familiar conditions. Some worlds may have skies so dense that standing beneath them would feel like being at the bottom of an ocean. Super-Earths, with masses several times that of our planet, could retain thick atmospheres rich in hydrogen. The sky on such a world might appear pale and milky, light scattering endlessly through layers of gas. The pressure at the surface would be immense, compressing life into forms adapted to weight and constraint. Sound would travel differently. Flight, if it existed, might be effortless. Evolution would sculpt bodies and minds around density rather than freedom. Other worlds might have skies that are thin, fragile, barely present. A planet, clinging to the edge of habitability, could host a tenuous atmosphere that offers little protection from radiation. The sky would be dark even at midday, stars visible against a blackened backdrop. Life here would be hardened, shielded, perhaps living underground or beneath ice. The sky would not nurture life, but challenge it constantly, shaping resilience into every organism. When James Webb analyzes the atmospheres of distant planets, it is not just detecting gases, it is reading these stories. Each absorption line in a spectrum is a clue to the color of the sky, the chemistry of the clouds, the dynamics of weather on a world light years away. Oxygen suggests not just breathable air, but blue skies and ozone shields. Methane hints at complex chemistry and possible biological cycles. Carbon dioxide speaks of greenhouse warming and climate regulation. Together, these signals allow us to imagine what it might feel like to stand there, to look up. And looking up is essential. The sky is where a civilization first encounters the cosmos. It is where questions begin. On Earth, our ancestors tracked the stars long before they understood atoms. The sky shaped myth, navigation, agriculture, and time itself. On another world, under another sky, Intelligence would grow in dialogue with its atmosphere. The questions asked by alien minds would be framed by what they see above them. A sky dominated by constant cloud cover might delay astronomy, hiding the stars for millennia. A sky clear and thin might reveal the universe with startling clarity, accelerating scientific curiosity. A planet with multiple moons could produce complex tidal patterns and dramatic night skies filled with motion. These environmental factors would influence not just biology but culture, philosophy, and technology. Alien skies may also host phenomena unknown on Earth. Lightning storms of unimaginable scale, driven by thick atmospheres and powerful convection. Auroras spanning entire hemispheres, fueled by intense magnetic interactions with active stars. Clouds of metallic vapor on ultra-hot worlds, where iron rains from the sky. These are not fantasies. They are predictions grounded in physics, already supported by observations. Such skies challenge our Earth-centered imagination. They force us to let go of the assumption that life requires familiarity. Instead, they invite us to recognize adaptability as the true constant of biology. Life does not seek comfort. It seeks gradients, differences in energy, chemistry, and structure that can be exploited. Alien skies provide those gradients in countless forms. Imagining a living world beyond Earth also means confronting scale. The sky of an exoplanet may appear larger or smaller depending on gravity and atmospheric thickness. On a low-gravity world, mountains could rise higher, clouds could tower further, storms could span continents. On a high-gravity world, the sky might feel close, pressing down, intimate and heavy. These differences would shape not only ecosystems but psychology. The sense of openness, confinement, vastness, or shelter would be written into the minds of intelligent beings. Consider color. Earth's blue sky is a consequence of Rayleigh scattering, favoring shorter wavelengths. But change the star's spectrum, or the atmosphere's composition, and the sky's color changes. A planet orbiting a cooler star might have a green or yellow sky. One with abundant aerosols might have a white or gray dome. On a world with unusual atmospheric chemistry, the sky could appear purple, brown, or even black. Color perception itself might evolve differently. Tuned to the dominant wavelengths of light, these skies would shape art, symbolism, and meaning. What does heaven mean on a world where the sky is opaque? What does darkness signify on a planet without night? Language itself would evolve in response to atmospheric realities. Metaphors we take for granted would have no equivalent elsewhere. Yet beneath all this diversity lies a shared truth. Skies connect worlds to their stars and to the wider galaxy. They are interfaces between the surface and the cosmos. Through them, energy flows. Through them, information arrives. Through them, life negotiates its place in the universe. James Webb's revelations about potentially living planets are powerful because they allow us to imagine these interfaces with unprecedented clarity. We are no longer speculating in the abstract. We are grounding imagination in data. We are beginning to see not just dots of light, but environments. This shift matters deeply. For centuries, alien worlds were imagined either as mirrors of Earth or as monstrous extremes. Now we can imagine them as coherent systems, governed by physics, yet open to creativity. Alien skies become not symbols of otherness, but expressions of universal processes unfolding in different contexts. There is also a humbling realization embedded in this imagination. Earth's sky, which we often take for granted, is itself extraordinary. Its transparency, its balance, its protective layers, all are finely tuned outcomes of geological and biological history. Seeing alien skies through scientific imagination helps us see our own more clearly. Familiarity dissolves into appreciation, and appreciation leads to responsibility. If life elsewhere exists beneath alien skies, it will face the same vulnerabilities we do. Atmospheres can be lost. Climates can destabilize. Skies can turn hostile. Imagining alien worlds is not escapism, it is perspective. It reminds us that habitability is not permanent. It is maintained, sometimes precariously. This awareness reshapes how we think about exploration. When we search for life, we are not just searching for novelty. We are searching for kinship in fragility. We are asking whether the universe has found multiple ways to balance chemistry, energy, and time long enough for consciousness to emerge. Standing beneath an alien sky, even in imagination, changes us. It stretches empathy beyond species and planet. It encourages humility, curiosity, and patience. It invites us to think in planetary timescales rather than human ones. For a science-loving audience, this is not mere wonder. It is an invitation to deeper inquiry. Every imagined cloud layer raises questions about atmospheric dynamics. Every hypothetical color invites analysis of scattering and absorption. Every speculative ecosystem demands thermodynamic plausibility. Imagination becomes a tool of understanding, guided by evidence. As telescopes improve, imagination will become increasingly constrained by data, and that is a good thing. The universe is more interesting than our fantasies. Reality has already proven richer, stranger, and more subtle than science fiction predicted. Alien skies will likely surprise us not by how exotic they are, but by how logically they arise from simple rules applied under different conditions. In imagining living worlds beyond Earth, we are rehearsing a future moment, a moment when we may look at a spectrum and know, with confidence, that life is shaping an atmosphere far away. When that happens, the image that will linger is not a creature's face, but a sky, an atmosphere altered by metabolism, by growth, by survival. That sky will be proof that life is not confined to one pale blue dot. It will be evidence that the universe is capable of producing multiple theaters where matter becomes aware of itself. And when we imagine standing beneath that sky, we are not escaping Earth. We are expanding our sense of belonging. We are recognizing that our planet is one expression of a broader cosmic possibility. Alien skies remind us that the universe is not silent. It is atmospheric. It is dynamic. It is alive with processes that, under the right conditions, give rise to living worlds. To imagine those skies is to prepare ourselves for a profound shift, not just in science but in identity. We are not merely observers of the cosmos. We are participants in a story that may be unfolding on countless worlds, each beneath its own sky, each fragile, each precious, each shaped by light falling through gas onto a surface where life dares to persist. And that realization, more than any image or statistic, is what truly changes everything. 9. Dark matter, the hidden architecture of reality. Most of what exists in the universe is invisible, not metaphorically invisible, not hidden behind distance or dust, but fundamentally unseen. It does not glow. It does not reflect light. It does not announce itself in any direct way. And yet, without it, galaxies would not hold together, stars would not form as they do, and the large-scale structure of the cosmos would unravel. This unseen presence is what we call dark matter, and it is not a footnote to reality. It is the scaffolding on which reality is built. When we look up at the night sky, we see light that has traveled for years, centuries, sometimes billions of years to reach us. We see stars, nebulae, galaxies, luminous islands in a vast cosmic ocean. But what we are seeing is only a small fraction of what is actually there. The visible universe is like foam on the surface of a deep sea. Dark matter is the water beneath. The first hints of dark matter did not come from speculation or philosophy, but from careful measurement. Astronomers noticed something unsettling when they measured how fast stars orbit the centers of galaxies. According to the laws of gravity, stars farther from the center should move more slowly, just as planets farther from the sun orbit more gently. But they didn't. Stars at the edges of galaxies were moving far too fast, as if pulled by gravity from matter that could not be seen. The implication was unavoidable. There was more mass than light could account for, much more. At first, scientists considered mundane explanations. Perhaps our understanding of gravity was incomplete. Perhaps there were vast amounts of dim, ordinary matter cold gas, dust, faint stars hiding in the dark. But as observations improved, these explanations fell apart. The missing mass was too abundant, too smoothly distributed, too influential to be explained by anything familiar. Dark matter was not just present, it dominated. Today we estimate that roughly 85% of all matter in the universe is dark matter. Everything we know, stars, planets, people, atoms, makes up a mere sliver of the cosmic inventory. We are not living in a universe of matter, but in a universe of dark matter with some matter sprinkled on top. This realization forces a profound shift in perspective. The structures we see are not primary, they are secondary. Galaxies form where dark matter clumps first. Gas falls into these gravitational wells. Stars ignite within them. Planets emerge later still. Dark matter does not simply coexist with visible matter, it orchestrates it. Imagine the universe shortly after the Big Bang. Matter and radiation were almost evenly distributed, with tiny fluctuations in density. On their own, these fluctuations were too small to form galaxies quickly. But dark matter, immune to radiation pressure and interacting primarily through gravity, began to clump early. These clumps grew, pulling ordinary matter along with them. Without dark matter, the universe might still be a diffuse fog, never coalescing into the structures necessary for life. In this sense, dark matter is the hidden architecture of reality. It is the framework upon which everything else is built, even though it remains unseen. Yet, despite its central role, dark matter remains deeply mysterious. We do not know what it is made of. It does not interact with light, making it extraordinarily difficult to detect directly. It passes through ordinary matter almost effortlessly, as if the atoms that make up our bodies were mostly empty space, which in fact they are. Scientists have proposed many candidates: weakly interacting massive particles, axions, sterile neutrinos, and other exotic entities that extend beyond the standard model of particle physics. Entire experiments have been built deep underground to shield sensitive detectors from cosmic noise, waiting patiently for the faintest whisper of interaction. So far, dark matter has remained silent, but its silence is not absence. Its presence is written everywhere in the cosmos. We see it in gravitational lensing, where massive clusters of galaxies bend light from objects behind them, creating arcs and distortions. The amount of bending reveals mass, far exceeding what we can see. We see it in the cosmic microwave background, the faint afterglow of the Big Bang, whose subtle patterns encode the influence of dark matter on the early universe. We see it in simulations that reproduce the large-scale web of galaxies only when dark matter is included. The universe, it turns out, is woven like a cosmic spiderweb, with filaments of dark matter stretching across vast distances, intersecting at dense nodes where galaxies cluster. This cosmic web defines where matter flows, where stars form, where potential habitats for life might arise. Without dark matter, there would be no Milky Way as we know it, no stable galactic disk, no long-lived stars like our Sun, no quiet corner of the universe where life could evolve slowly, protected from chaos. Dark matter is not just a background feature, it is a prerequisite for complexity. This raises a profound question. If dark matter shapes the universe so fundamentally, why does it remain so aloof? Why does it interact so weakly with the matter we know? One possibility is that dark matter belongs to an entire hidden sector of physics, with its own particles and forces, largely decoupled from our familiar world. If so, reality is far richer than our current theories suggest. What we perceive as the universe may be only one layer of a deeper structure. This idea resonates beyond physics. It challenges our intuition about what is real. We tend to equate reality with what we can see, touch, or measure directly. Dark matter reminds us that influence does not require visibility, that the most important forces shaping existence may operate quietly, patiently, beyond immediate perception. There is a philosophical echo here. Human history, too, is shaped by invisible architectures, Ideas, values, systems, incentives that guide behavior more powerfully than surface appearances. Dark matter is a cosmic analogy for this truth. The universe, like society, is structured by what lies beneath. For those fascinated by the search for life beyond Earth, dark matter adds another layer of wonder. The distribution of dark matter determines where galaxies form, how they evolve, and how stable their environments are. In this way, dark matter indirectly influences the likelihood of habitable planets existing at all. Galaxies with too little dark matter may not hold together long enough for stars to form steadily. Those with too much may experience violent interactions that disrupt planetary systems. The balance matters. Dark matter sets the stage, but the details determine whether life gets a chance. Even on the scale of individual galaxies, dark matter halos act as guardians. The Milky Way is embedded in a massive halo of dark matter that extends far beyond its visible disk. This halo stabilizes the galaxy, reducing the frequency of catastrophic interactions and helping maintain an environment conducive to long-term evolution. Our existence is linked, indirectly but undeniably, to this invisible presence. And yet, for all its importance, dark matter does not care about us. It does not react to our presence. It does not participate in chemistry, biology, or consciousness as far as we know. It is indifferent, but not irrelevant. This indifference is part of what makes the universe both humbling and awe-inspiring. We are not the center. We are not even made of the dominant substance. We are guests in a cosmos structured by something we barely understand. There is a temptation to feel diminished by this realization. But there is another way to see it. The fact that beings composed of such a small fraction of the universe's matter can nonetheless uncover the existence of the rest is extraordinary. We are minor players who have learned to read the rules of a vast game. Dark matter has never been observed directly, but its fingerprints are everywhere. This is a triumph of inference, of reasoning from effect to cause. It is a reminder that science advances, not just by seeing, but by understanding what must exist for what we see to make sense. This has implications beyond cosmology. It speaks to the power of human curiosity and patience. Dark matter was not discovered by accident. It was revealed through decades of careful measurement, skepticism, and willingness to accept uncomfortable conclusions. That willingness is a defining feature of scientific progress. The universe does not owe us simplicity. It does not conform to intuition. Dark matter is a testament to that. It forces us to expand our models, to imagine entities that do not fit neatly into existing categories. As we push further, we may discover that dark matter is not a single thing, but many, or that it interacts in subtle ways we have not yet detected, or that it points to a deeper revision of gravity itself. Each possibility carries profound consequences for our understanding of reality. And here, science meets philosophy again. If most of reality is hidden, then humility is not optional. Certainty must be provisional. Knowledge must remain open-ended. Dark matter teaches us that the universe is under no obligation to reveal its full inventory easily. This lesson resonates with the broader search for life and meaning. Just as dark matter shapes galaxies invisibly, there may be forms of life, intelligence, or organization in the universe that we have not yet learned how to detect. Absence of evidence is not evidence of absence, especially in a cosmos where the dominant components are silent. Dark matter also reframes the idea of isolation. We often ask whether we are alone in the universe, but in another sense we are already surrounded by something vast, pervasive, and unseen. We coexist with dark matter at every moment it passes through our planet, our bodies, our instruments, unnoticed. The universe is already more crowded than it appears. This does not diminish the mystery of life elsewhere. It deepens it. It suggests that reality is layered, that what we experience directly is only one stratum of a more complex whole. Life may occupy another layer still, waiting for the right tools, the right questions, the right humility to be discovered. In contemplating dark matter, we are reminded that understanding often begins with discomfort, with anomalies that refuse to go away, with data that does not fit. dark matter was once such an anomaly. Today, it is a cornerstone of cosmology. Tomorrow, it may be the gateway to an even deeper revolution. And that is the enduring power of this idea. Dark matter is not just a solution to a problem. It is an invitation to rethink what we mean by reality itself, to accept that the universe is not only stranger than we imagine, but stranger than we can imagine until evidence forces our imagination to grow. In the context of a planet that may harbor life, shaped by a galaxy sculpted by dark matter, this realization carries a quiet poetry. Life, fragile and rare, emerges within structures built by unseen forces. Consciousness arises in a universe whose dominant substance does not think, does not feel, does not know it exists. And yet, through us, the universe becomes aware of its own hidden architecture. Dark matter may never be something we can touch or see, but it has already changed everything. It has shown us that reality is deeper than appearance, that structure precedes surface, and that the most important ingredients of existence may operate in silence. To understand dark matter is not just to solve a scientific puzzle. It is to accept a new relationship with the cosmos, one defined not by mastery, but by curiosity, humility, and in that sense, dark matter is not merely out there, shaping galaxies. It is also within our story, shaping how we understand our place in a universe far richer and far more mysterious than we once believed. Black holes, destruction, creation, and cosmic rebirth. Black holes have always captured the human imagination because they embody extremes of gravity, of density, of mystery. They are points where matter collapses into infinitesimal concentration, where space and time themselves are warped beyond recognition, where the familiar rules of physics give way to paradox. And yet, for all their destructive power, black holes are not merely cosmic vacuums sucking up everything around them. They are agents of creation, engines of transformation, and catalysts for rebirth on scales both subtle and monumental. To understand them is to confront the universe at its most uncompromising, and in doing so to confront ourselves. A black hole begins as a star, massive and burning, struggling against its own gravity. For millions of years, the star exists in a delicate balance. Outward pressure from nuclear fusion counteracts the relentless inward pull of gravity. This balance allows the star to shine, to host fusion that creates the elements, carbon, oxygen, iron, that are the building blocks of planets and life. Yet, when the star exhausts its fuel, the balance collapses. Gravity wins. The star implodes, its core compresses into a singularity, a point of infinite density where conventional physics ceases to operate, and the outer layers may explode outward in a supernova, scattering enriched matter across space. In that moment, destruction and creation are inseparable. The black hole that remains is both an end point and a beginning. It represents the end of a star's life, yet it seeds the galaxy with the elements necessary for new stars, planets, and potentially life itself. In a sense, black holes are cosmic recyclers, transforming one state of matter into another, maintaining the ongoing cycle of the universe. The singularity itself is the ultimate unknown. Here, densities and energies reach extremes that defy intuition. Space curves upon itself. Time slows, stretching to infinity at the event horizon. The event horizon, the boundary beyond which nothing can escape, marks a threshold between the familiar and the unknowable. Cross it, and no information returns. Yet the horizon is not simply a line of destruction. It is a surface where physics and information interact in subtle ways. Recent theories suggest that even as matter falls into a black hole, information may not be lost entirely. The universe may encode it at the horizon, preserving the history of infall in ways we are only beginning to understand. Around black holes, matter behaves in astonishing ways. Gas spirals inward, forming luminous accretion disks that radiate tremendous energy across the electromagnetic spectrum. Friction and magnetic forces accelerate particles to nearly light speed, producing jets that shoot out perpendicular to the disk, extending across thousands of light years. These jets are not random. They redistribute energy and matter, influencing star formation and galaxy evolution. A black hole's activity can trigger the birth of new stars even as it devours its surroundings. Destruction and creation, entwined in a cosmic dance. Black holes also teach us humility about scale and time. The supermassive black holes that anchor the centers of galaxies, including our own Milky Way, contain millions or billions of times the mass of the Sun. Their gravitational influence shapes the motions of countless stars, the dynamics of entire galaxies, yet they occupy a volume minuscule compared to the space they dominate. A region no larger than the solar system can dictate the fate of billions of stars. It is a reminder that influence is not proportional to size. Small but concentrated forces can govern vast domains. Their lifetimes are similarly staggering. Black holes formed in the earliest epochs of the universe persist across billions of years. They witness cosmic history, absorbing matter, merging with other black holes, and radiating energy in patterns that slowly reshape galaxies. They are timekeepers of a kind, monuments to endurance in a universe defined by change. But black holes are not merely passive observers. They are laboratories for extremes, for physics that cannot be replicated on Earth. The event horizon is where general relativity and quantum mechanics collide, where our understanding of space, time, and information is tested to the limit. Hawking radiation, a theoretical emission caused by quantum effects near the horizon, suggests that black holes are not entirely permanent. They slowly evaporate over unimaginably long timescales, releasing energy and particles back into the cosmos. Even the most extreme concentrations of matter are impermanent. Destruction itself contains the seeds of transformation. This leads to a profound philosophical insight. Black holes embody the duality of existence. They are both annihilation and renewal. To approach one even theoretically is to accept that the universe contains processes beyond ordinary comprehension, where extremes are not anomalies but integral features of cosmic architecture. They remind us that endings are rarely final in a universe defined by cycles, feedback, and emergence. In thinking about life, intelligence, and human motivation, black holes offer lessons that extend beyond physics. They are emblematic of resilience and adaptation. Life emerges in fragile, transient conditions, yet it persists through cycles of creation and destruction, through mass extinctions, climate shifts, and planetary upheavals. Similarly, black holes endure across eons, absorbing, transforming, and shaping. They are reminders that longevity is not just a matter of resisting change, but of interacting with it in productive, generative ways. There is also a metaphorical power in their invisibility. Black holes are known not by what they emit, but by their influence on the surroundings. This mirrors human perception and understanding. Influence is often detected indirectly, by its effects, rather than by direct observation. Life on other worlds, or even unseen processes on Earth, may reveal themselves in subtle interactions, shifts, and anomalies rather than overt signals. Recognizing these hidden influences is part of scientific sophistication and intellectual humility. The interplay between black holes and galaxies underscores the importance of context. A black hole cannot exist in isolation. Its growth, behavior, and influence are inseparable from the larger structures it inhabits. Similarly, life, intelligence, and civilizations are inseparable from the systems that support them: planetary, ecological, and cosmic. The emergence of complexity requires both extreme forces and stabilizing environments, both chaos and order. Black holes also highlight the limitations of our perception. We tend to think of space as vast but empty, punctuated by stars and planets. Yet the universe is threaded with regions where gravity curves, time dilates, and energy behaves in unexpected ways. These regions are often invisible, detected only through indirect observation. The cosmos, much like knowledge itself, is largely hidden, requiring tools, imagination, and careful inference to perceive. What is unseen may dominate reality. The discoveries of recent years, including the first direct imaging of a black hole's shadow and the detection of gravitational waves from merging black holes, have expanded our understanding dramatically. Gravitational waves, ripples in the fabric of space-time, allow us to hear the universe, to sense collisions that occurred billions of years ago. Black holes, once theoretical curiosities, have become messengers, conveying information about extreme physics and cosmic history. They are both objects of mystery and instruments of revelation. And in the context of a universe where life may exist elsewhere, black holes acquire an additional dimension. Their activity influences star formation, galactic stability, and the dispersal of heavy elements necessary for planets. A supernova near a black hole may trigger new cycles of creation, scattering elements that will one day form water, carbon, and oxygen, the ingredients of life. The processes of destruction and rebirth are entwined, cosmic feedback loops that set the stage for habitability and evolution. Black holes, in a way, are the ultimate teachers of impermanence and possibility. They exist at the intersection of extremes: density, gravity, time, and energy. And yet, they are also bound by law. Their existence is dictated by the same equations that govern planetary orbits and stellar fusion. Yet their consequences challenge every intuition we have built. They teach us that understanding requires both respect for law and willingness to confront paradox. Even the concept of a singularity, the point at which matter is thought to compress infinitely, serves as a humbling reminder of the limits of knowledge. It is a place where our current theories break down, where questions outpace answers. Yet from this breakdown arises opportunity, the possibility of new physics, new insights into the fabric of space-time, and perhaps even new ways to think about emergence, complexity, and causality. Black holes also force us to confront the scale of cosmic time. Stars live millions to billions of years. Galaxies evolve over billions more. Black holes endure across cosmic epochs, accumulating mass, merging, radiating energy. Human lifespans, even in the context of civilization, are mere instants. And yet, in that instant, we can comprehend, model, and even visualize these extreme objects. Consciousness, fragile and brief, becomes capable of understanding forces that operate over scales of density, energy, and time far beyond our own. This is one of the profound marvels of intelligence. The dual nature of black holes as destructive singularities and as creative engines also resonates with human experience. Growth often requires collapse. Innovation arises from the breakdown of old structures. Creativity is inseparable from the willingness to confront limits, to embrace extremes, to accept uncertainty. Black holes embody this principle on the grandest possible scale. They are cosmic teachers of transformation, revealing that endings are not annihilation, but potential. And there is beauty in that extremity. The accretion disk glowing with X-rays, the jets extending light years into space, the gravitational lensing that distorts starlight, all are manifestations of order arising from chaos, symmetry emerging from collapse. Even in death, a star can produce phenomena of sublime grandeur. Black holes remind us that the universe has no obligation to be gentle, yet can still be profoundly aesthetic. In contemplating black holes, we also confront the nature of observation itself. No one has entered a black hole to report back. We know them entirely through indirect effects. Motions of nearby stars, emissions from accretion disks, distortions of light, gravitational waves. In life and science, much of what is most important may be inferred rather than directly perceived. Influence, consequence, and presence often precede detection. Black holes amplify this lesson across cosmic scale. Finally, black holes connect us to cycles of rebirth on a universal level. Galaxies grow and evolve, stars form and die, elements are synthesized and dispersed. Black holes participate in these cycles, regulating galactic environments, triggering star formation, and perhaps even seeding conditions for life in distant corners. They are reminders that destruction is rarely absolute, that the universe is a system of transformation in which endings are rarely final, and beginnings often arise from collapse. For a civilization pondering its place in the cosmos, black holes embody both humility and inspiration. They show that survival, growth, and knowledge occur within contexts far larger than oneself. They demonstrate that extremes can coexist with law, that danger can produce beauty, and that endings can give rise to creation. They challenge imagination, expand understanding, and ultimately connect the processes of life, matter, and consciousness to the deepest mechanisms of the universe. Black holes are not merely curiosities or threats. They are engines of cosmic history, anchors of galaxies, crucibles of energy, and catalysts for transformation. They are simultaneously destructive and generative, ephemeral and eternal, invisible yet profoundly influential. To study them is to confront the universe at its limits, to confront paradox, and to recognize that life, intelligence, and meaning are emergent phenomena in a cosmos that continuously collapses and rebuilds itself. In this sense, black holes are not separate from the story of life or the discovery of habitable worlds. They are part of the same narrative: matter, energy, time, and space interacting in ways that create both danger and possibility, destruction and creation, endings and rebirth. To understand black holes is to understand one of the most powerful forces shaping the cosmos, and to glimpse how the universe orchestrates cycles of emergence, resilience, and transformation on a scale that defies ordinary comprehension. They remind us, ultimately, that every ending contains the seeds of a beginning, that even in the shadow of annihilation, creation is possible, and that the cosmos, in all its violence and mystery, remains a theater for emergence, complexity, and life. 11. Nebulae, where death becomes new beginnings. Nebulae are among the most visually arresting structures in the cosmos, yet their beauty is only a fragment of their deeper significance. They are not merely clouds of gas and dust suspended in the void, painted with the colors of hydrogen, oxygen, and sulfur. They are crucibles of transformation, laboratories of cosmic alchemy, and theaters in which death becomes new beginnings. To observe a nebula is to witness the universe in a state of continual reinvention, a cycle in which the destruction of one star, the dispersal of matter, and the interplay of forces give rise to the seeds of countless new worlds. These clouds remind us that in the universe, as in life, endings are rarely absolute, and that every conclusion carries the potential for creation. Consider the life cycle of a star. Like living organisms, stars are born, age, and eventually die. Massive stars exhaust their nuclear fuel and explode as supernovae, scattering their enriched contents into the surrounding interstellar medium. These remnants, initially chaotic and violent, expand outward, colliding with ambient gas and dust, forming vast, glowing nebulae. The death of a star is not a simple disappearance. It is a transformative event that reshapes its environment, enriching it with elements that did not exist when the universe was younger. Carbon, nitrogen, oxygen, and iron, the fundamental building blocks of planets and life, are forged in stellar cores and liberated through these deaths, creating the material canvas from which new stars, planets, and eventually life itself can emerge. Nebulae are therefore both graveyards and nurseries. They are the tombstones of stars, but also the wombs from which new systems are born. In observing a nebula, we confront a paradox. We witness destruction, yet embedded within that destruction is the promise of creation. This duality mirrors processes on Earth, on scales from geology to biology, where cycles of decay, decomposition, and regeneration maintain the conditions for ongoing life. Cosmic and terrestrial processes converge in this principle. Creation and destruction are inseparable partners in the orchestration of complexity. The Orion Nebula, one of the most studied and photographed nebula, exemplifies this dynamic. Within its vast, turbulent clouds, regions collapse under gravity, forming protostars that will eventually ignite nuclear fusion. Surrounding these forming stars, disks of gas and dust coalesce, laying the foundation for planetary systems. In some regions, powerful stellar winds and radiation sculpt the nebula, eroding and compressing clouds, triggering further star formation. The nebula is alive in its dynamics, constantly reshaping itself and distributing energy and matter. Even the death of older stars within the region feeds the ongoing process, seeding new generations with enriched materials. Here, the universe demonstrates resilience and ingenuity, turning endings into beginnings on an immense scale. From a chemical perspective, nebulae are the crucibles of complexity. The shockwaves of supernovae, the ultraviolet radiation from massive stars, and the turbulence of interstellar gases catalyze chemical reactions that would be impossible in the quiet of empty space. Simple molecules combine into more complex structures, forming organic compounds that may ultimately contribute to the chemistry of life on planets yet to form. In this sense, nebulae are laboratories where nature experiments with the fundamental ingredients of biology, long before any conscious observer could recognize them as precursors to life. The colors of nebulas, often captured in breathtaking images, are not arbitrary. They reveal the physical processes at work. Hydrogen glows red when ionized, oxygen emits green or blue hues, sulfur fluoresces in deep red. These emissions are not merely aesthetic, they are signatures of energy transfer, radiation, and chemical interaction. By studying these signatures, scientists reconstruct the history of matter within the nebula, discerning the life cycles of stars, the composition of primordial material, and the potential for future star and planet formation. The nebula, in essence, is a cosmic archive, preserving records of transformation across time and space. Nebulae also remind us of the interconnectedness of cosmic processes. The death of one star influences the birth of another. The dispersal of elements from one supernova becomes the raw material for countless planetary systems. The gravitational interactions within a nebula dictate the trajectories of emerging stars, shaping clusters and eventually galaxies. Nothing exists in isolation. Every nebula is part of a larger tapestry, woven from the interactions of mass, energy, and time. To observe it is to perceive the universe as a system of interdependent processes, where outcomes emerge from interaction rather than from singular events. Beyond their physical properties, nebulae challenge our perception of scale and time. These clouds can span dozens to hundreds of light years, evolving over hundreds of thousands to millions of years. The processes within them unfold on temporal and spatial scales far beyond human intuition, yet their influence reaches across the cosmos. Stars formed within a nebula today may host planets that, billions of years later, develop life. The events we observe in a nebula now may have shaped regions of the galaxy whose effects will be felt long after the Sun has completed its own life cycle. In this sense, nebulae are monuments to continuity and persistence, a reminder that the universe operates on timescales that dwarf human existence, yet in ways that are deeply consequential for life and structure. Nebulae also invite reflection on the fragility and contingency of life. The elements that compose living organisms, carbon, oxygen, nitrogen, phosphorus, are produced in stars and distributed through supernovae. Without the processes that generate and recycle these elements, life as we know it could not exist. The universe is generous, but that generosity is mediated by processes that are violent, precarious, and contingent. Nebulae are visible evidence of this tension between fragility and abundance. They demonstrate that life emerges not in spite of cosmic violence, but because of it, and that our own existence is intimately tied to events that occurred long before the Earth formed. At the same time, nebulae illustrate the principle of emergence. From turbulent clouds of gas and dust, structured systems arise. Gravity, pressure, magnetic fields, and radiation interact to produce stars, planets, and ultimately the potential for life. Order arises spontaneously from chaos, guided by natural laws but unpredictable in detail. This is a fundamental lesson for science and philosophy alike. Complexity is not imposed externally, but emerges from the interactions of simpler components over time. Nebulae provide a cosmic laboratory for understanding this principle in its most magnificent form. For those contemplating the discovery of exoplanets with potential for life, nebulae are particularly meaningful. Every planet orbiting a distant star is, in some sense, a product of nebular processes. The composition of its atmosphere, the availability of water, the presence of elements necessary for biochemistry, all trace back to stellar evolution and the dispersal of matter within nebulae. When James Webb or other observatories detect signatures of habitability or even life, we are witnessing the consequences of nebular alchemy that unfolded millions or billions of years earlier. Nebulae are the deep time preconditions for habitability, the invisible laboratories whose results are revealed in distant planetary systems. Nebulae also teach us to embrace paradox. They are places of death and birth, destruction and creation, chaos and structure. They are turbulent and ordered simultaneously. They operate on scales that are incomprehensibly vast, yet their processes directly enable the minute phenomena of life on planets. They are reminders that the universe is rarely binary, rarely simple, and that understanding requires comfort with complexity and contradiction. Moreover, nebulae encourage humility and wonder. The physical processes that shape them, the balance of gravity and pressure, the influence of magnetic fields, the interaction with radiation, are governed by universal laws that we can comprehend, yet the specific outcomes are unpredictable. The shapes, colors, and dynamics of any given nebula are unique, unrepeatable, and ephemeral in cosmic terms. They remind us that the universe contains beauty and order without needing to accommodate human desire, that creativity is inherent in natural processes, and that our role as observers is to recognize patterns, infer mechanisms, and marvel at existence. In contemplating nebulae, we also confront time in a non-linear way. A nebula observed today may contain stars forming now, stars formed millions of years ago, and remnants of stars that died eons before. Light from distant nebulae can take thousands of years to reach us, meaning we see them not as they are, but as they were. The past is imprinted on the present, and the present is shaped by events we cannot yet observe. Nebulae are temporal palimpsests, layered with history, hinting at futures that cannot yet be realized. They teach patience and perspective, encouraging us to expand our sense of time beyond human scale. Nebulae are also laboratories for imagination. The intricate filaments, luminous pillars, and diffuse clouds evoke forms that seem both alien and familiar. They invite us to envision worlds forming within their folds, planets orbiting newly ignited stars, and possibly life emerging under alien skies. Scientific imagination is grounded in observation, yet it flourishes in the space between known physics and creative hypothesis. Nebulae provide the canvas for this interplay, bridging empirical data and wonder, reason, and speculation. Furthermore, nebulae underscore the principle of recycling in the universe. Nothing is truly lost. Matter transformed in one context is reused in another. Stars die, elements disperse, new stars and planets emerge. Even the interstellar dust expelled from supernovae can condense into future solar systems. This principle of transformation mirrors ecological and biological cycles on Earth, where decomposition, nutrient cycling, and succession sustain life. The universe operates on similar laws, scaled across light years and millions of years, demonstrating that creation and destruction are inseparable and mutually reinforcing. In the context of cosmic philosophy, nebulae prompt reflection on purpose and contingency. They operate without intent, yet their processes produce conditions that allow consciousness, life, and complexity to arise. Order emerges from apparent chaos, structure from turbulence, possibility from death. Nebulae teach us that the universe is capable of generating meaning and habitability without design, that natural laws inherently produce environments where complexity can flourish. Our own existence is an emergent consequence of these processes, linking us intimately to the stars and the clouds from which they formed. For scientists and explorers, nebulae are both laboratories and beacons. They guide our understanding of stellar evolution, chemical enrichment, and planetary formation. They inform models of habitability and the potential for life beyond Earth. Every observation of a nebula deepens our knowledge, challenges our assumptions, and inspires new questions. They are reminders that the universe is dynamic, evolving, and perpetually creative, and that our investigations are part of an ongoing dialogue with these processes. Ultimately, nebulae are more than astronomical objects. They are metaphors for resilience, transformation, and continuity. They demonstrate that endings are rarely terminal, that destruction is productive, and that life and complexity are inseparable from processes of change. In contemplating nebulae, we learn to see the universe as a system of perpetual renewal, where death gives rise to possibility, and where the cycles of matter and energy create the conditions for life to emerge again and again. Nebulae invite us to stand in awe, not only of their beauty but of the principles they embody, the alchemy of elements, the interplay of forces, the emergence of structure from chaos, and the transformation of endings into beginnings. They remind us that the universe is a theater of perpetual creation, and that our existence is the fruit of countless cycles of stellar death and rebirth. In every glowing cloud, every filament of dust, every turbulent swirl, we witness the cosmos, teaching its deepest lesson, that life and complexity are born from transformation, that beginnings arise from endings, and that the universe is, at its core, a luminous, ever-changing tapestry, where death becomes the seed of all new possibilities. 12. Time dilation and the illusion of now. Time is the framework in which we live our lives, yet it is far less absolute than our intuition suggests. Every day we experience it as a steady flow, a constant march from past to future. We mark it with clocks, calendars, and rituals. We measure seconds, minutes, and hours as though they were universal, immutable. But the universe has taught us that this sense of now is an illusion, a subjective experience anchored in our particular frame of reference. Through the lens of Einstein's theory of relativity, time is malleable, stretching and compressing depending on motion, gravity, and the scale at which we observe reality. To explore this is to confront a profound truth, that the present, the now we cling to, is not a fixed point in the cosmos, but a local, relative phenomenon, intimately connected to the structure of space, the motion of matter, and the forces that govern the universe. Einstein revolutionized our understanding of time by demonstrating that it is not independent from space. Space and time are intertwined, forming a four-dimensional continuum we call space-time. Movement through space affects movement through time. A clock moving rapidly relative to an observer ticks more slowly. A clock deep within a gravitational well ticks more slowly than one far from massive objects. These effects, known as time dilation, have been confirmed experimentally countless times, from precise measurements of atomic clocks on airplanes to satellites orbiting Earth. They are not speculative curiosities, they are measurable, predictable, and essential to the functioning of technologies like GPS. Time dilation is not merely a technical detail. It is a window into the fundamental nature of reality. Consider an astronaut traveling near the speed of light. To them, seconds pass normally, yet when they return to Earth, decades may have elapsed for those who remained behind. The now they experienced was different from the now experienced by anyone else. The universe does not privilege a single present. Each observer carries their own version of the moment. Past and future are not universal absolutes, but relative constructs. The flow of time is a local experience, tethered to specific positions and motions within space-time. Gravity amplifies this effect. The stronger the gravitational field, the more space-time is curved, and the slower time passes, relative to regions of weaker gravity. Near a black hole, for instance, time stretches dramatically. An observer far away might see objects near the event horizon frozen in motion, their evolution slowed to an almost imperceptible crawl. For the objects themselves, time feels normal. They continue to evolve, to interact, to experience the universe. But their now is radically different from that of distant observers. Here, time is not universal. It is a property of perspective, a function of location and circumstance. This relativity of time has profound implications for our understanding of existence. What we perceive as linear progression, birth, growth, decay, is not a fundamental property of the universe, but a construct emerging from our particular vantage point. The sequence of events is relative, shaped by motion and gravity. Cosmic events, from the collision of galaxies to the formation of stars, unfold across scales that make human experience of time nearly meaningless. A star forms over millions of years, yet to a particle near a black hole, those millions could pass as a few fleeting moments. Our sense of urgency, of progression, is tied not to universal time, but to our local frame of reference. In contemplating planets beyond our solar system, particularly those with the potential for life, time dilation introduces subtle yet fascinating considerations. Imagine a planet orbiting a star far more massive than the Sun, or skimming the edge of a dense stellar remnant. Clocks there would tick differently than on Earth, seasons would stretch or compress, and the rhythm of biological cycles might be altered. Life, if it exists, would experience a now shaped by its gravitational and orbital circumstances. Consciousness itself, our perception of past, present, and future, would be molded by the curvature of space-time. The universe becomes not a uniform stage, but a patchwork of temporal experiences, each legitimate within its own domain. Even on Earth, the effects are measurable. Atomic clocks flown on airplanes tick slightly differently than those remaining on the ground. Satellites in orbit experience time slightly faster than observers below. These tiny differences, when accumulated over months and years, must be accounted for to maintain the precision of navigation systems. Time, in other words, is not a constant backdrop. It is a dynamic variable shaped by motion, position, and energy. The illusion of a single shared now is a practical convenience, not a fundamental truth. This understanding challenges deep-seated intuitions. We tend to imagine the universe as a series of events unfolding sequentially, a cosmic movie with a single frame shared by all observers. Relativity tells us that this movie is more like a hologram, each observer carrying their own projection, each moment simultaneous in some frames, staggered in others. Cause and effect remain consistent locally, but the global sequence is not uniquely defined. Time is flexible, a property of perspective rather than an absolute ruler. From a philosophical perspective, this relativity of now has profound implications. Our notions of memory, anticipation, and experience are rooted in a personal, local understanding of time. We remember a past that has already passed in our frame and anticipate a future that has yet to occur, yet elsewhere in the cosmos. Those moments may be experienced differently. The universe is far more pluralistic than our intuition suggests, containing countless nows coexisting across space and gravity wells. Reality, in this sense, is a network of perspectives, a tapestry of temporal experiences woven together by the structure of space-time. For life and consciousness, these effects are subtle but significant. Evolution operates on timescales vastly longer than human lifespans, yet the distribution of matter and energy in the universe, shaped by gravitational time dilation, indirectly influences the conditions for life. Star lifetimes, planetary climates, and the stability of orbits are all functions of mass and motion, which in turn shape the experience of time locally. Life is not independent of time, it is embedded within it, arising from and constrained by the malleability of space-time itself. Time dilation also reframes our understanding of cosmic observation. When we look at distant galaxies, we are looking into the past, sometimes billions of years ago. The light arriving at our telescopes has traversed vast stretches of space and time, its history encoded in photons. For a civilization orbiting an exoplanet discovered by James Webb, observing Earth with their own instruments, they might see the planet in a different epoch. They're now intersecting ours in ways that challenge our conception of simultaneity. Communication and perception across the cosmos are bound not only by distance, but by the relativity of time itself. The illusion of shared simultaneity dissolves, replaced by a more nuanced understanding of causality and perspective. Moreover, the concept of time dilation invites reflection on the fleeting nature of human experience. A single human lifespan is brief relative to stellar evolution, galactic dynamics, and the age of the universe. Yet consciousness allows us to perceive and interpret these vast processes, compressing eons into comprehension. In this sense, relativity enhances our appreciation of temporality. It teaches that while our personal experience is finite and bounded, it is sufficient to engage with the infinite complexity of cosmic phenomena. The universe is patient. Our observation is fleeting, yet profoundly meaningful within its own context. Time dilation also intersects with our imagination and speculation. Science fiction has long explored the possibilities of near light speed travel, relativistic effects on aging, and communication delays across the stars. These narratives are grounded in physics, yet they inspire us to reconsider our expectations of linearity, simultaneity, and permanence. They invite us to explore life, consciousness, and society within frameworks radically different from earthbound intuition, challenging assumptions and expanding our mental horizons. Relativity, in this sense, is not merely a physical principle, it is a tool for cognitive expansion. Even within our solar system, relativistic effects are present, near massive planets or in strong gravitational fields. Time passes differently. Astronauts on long-duration missions experience minute differences in elapsed time compared to those on Earth. These small effects, imperceptible in daily life, scale dramatically in more extreme environments. Imagine approaching a neutron star or a black hole, where seconds for an observer far away correspond to hours, years, or millennia for one nearby. The illusion of a universal now collapses entirely. Observers are each embedded in their own temporal domain, their experience is valid and real, yet not identical. This understanding also affects our conception of causality. Events that appear sequential from one vantage point may be simultaneous or even reversed from another. Cause and effect remain internally consistent for each observer, but globally the notion of absolute ordering is invalid. Time is local, contingent, and relative, a property emerging from the geometry of space-time rather than a universal flow. Our perception of past, present, and future is therefore a function of position, motion, and gravitational context, not an intrinsic property of reality. From a human perspective, this has deep philosophical resonance. We are accustomed to thinking in terms of linear progression, deadlines, aging, and memory. Relativity teaches that these concepts are context-dependent, contingent on frame of reference. It encourages flexibility in thinking, humility in assumptions, and openness to the surprising ways that reality can manifest. Time is not an enemy, a fixed measure to be conquered, but a medium in which experience unfolds shaped by forces far beyond human control. In the search for life beyond Earth, time dilation introduces fascinating possibilities. Civilizations on planets orbiting massive stars, or in dense stellar environments, may experience life at a rhythm fundamentally different from our own. Their perception of past and future may be compressed or expanded relative to ours. Their biological and technological evolution would be intimately connected to the curvature of space-time, illustrating once again that life is inseparable from the cosmic context in which it arises. The universe is not uniform in its temporal experience. It is a mosaic of nows, each shaped by position, mass, and motion. Furthermore, time dilation underscores the interconnectedness of all things. Gravity, motion, and mass do not simply shape physical trajectories, they shape experience itself. The structure of the cosmos, from black holes to neutron stars to planetary systems, defines the rhythms of life, the evolution of matter, and the unfolding of consciousness. Time is not merely a passive dimension, it is an active participant in the drama of existence, influencing events, processes, and possibilities across scales unimaginable. Ultimately, the illusion of now invites us to expand our empathy and imagination. Just as we understand that distant observers may experience time differently, we can appreciate that life, consciousness, and experience are relative in many ways, shaped by context, circumstance, and perspective. This is not only a scientific insight, but a philosophical one. Reality is a tapestry of experiences, each locally coherent, yet globally diverse. To inhabit one temporal frame is to witness only part of a much larger, richer structure. Time dilation reminds us that the cosmos is more flexible, more nuanced, and more astonishing than everyday perception suggests. It teaches patience, humility, and wonder. It places human experience within a broader framework, encouraging us to think beyond immediate moments, to see the unfolding of events across centuries, millennia, and eons. The now we cherish is a beautiful and fragile construct, real in its own frame, yet only one perspective among countless others. In contemplating distant worlds, black holes, or the galaxies themselves, The relativity of time reshapes our sense of possibility. It reframes what is achievable, what is observable, and what is meaningful. Life, intelligence, and discovery operate within this flexible medium, constrained and enabled by the geometry of space-time. Understanding this allows us to approach the universe not as a fixed, predictable stage, but as a dynamic, interactive environment in which perspective shapes reality and every observer experiences their own valid now. Time dilation, then, is more than a physical effect. It is a lens through which to view existence, a principle that challenges intuition, inspires imagination, and deepens understanding. It teaches that the present is relative, the flow of time is malleable, and the universe is a tapestry of intertwined temporal perspectives. By embracing this, we not only expand our comprehension of physics, but we also expand our capacity to appreciate the richness, diversity, and interconnectedness of reality itself. 13. Cosmic silence. The Fermi paradox revisited. The night sky is filled with stars, each a blazing sun, many accompanied by planets, some possibly similar to our own Earth. The universe, vast and ancient, seems almost certain to host life beyond our blue planet. Yet, as we look and listen, as we scan the heavens with radio telescopes and survey exoplanets with instruments like the James Webb Space Telescope, we are met with silence. This profound, almost haunting absence of contact is encapsulated in what has come to be known as the Fermi paradox. If life is common in the cosmos, if intelligent civilizations have had billions of years to arise and expand, then where is everybody? Where are the signs of other minds, other civilizations, other possibilities of communication? The paradox is not a single puzzle, but a web of interlocking questions, each exposing the fragility and contingency of life. On the one hand, we now know that planets are abundant. Surveys of distant stars reveal that rocky planets orbit in habitable zones more frequently than once imagined. The ingredients of life, water, carbon, nitrogen, oxygen, are pervasive, formed in the cores of stars and scattered across galaxies through nebulae and supernovae. Chemical precursors for life exist even in the depths of interstellar space. If the conditions for life are common, why has the universe remained silent? One possible answer lies in the inherent difficulty of emerging as a complex, intelligent species. Life may arise frequently, but the step from simple microorganisms to self-aware, technologically capable civilizations might be rare, precarious, or contingent. The history of life on Earth is a testament to this precariousness. For billions of years, life existed solely as microbes, limited to oceans and soils. Only through a series of extraordinary circumstances, a planet stabilized by its magnetic field, a moon moderating climate, a sun with steady output, a series of mass extinctions clearing ecological niches, did complex life emerge. Intelligence itself may be a rare evolutionary experiment, contingent upon a confluence of planetary, biological, and cosmic conditions that may be uncommon across the galaxy. Even when intelligence arises, survival is not guaranteed. Civilizations are fragile. Technology brings power, but also risk. Self-destruction through environmental degradation, nuclear conflict, or unforeseen technological catastrophes may curtail longevity. The timescales for interstellar communication or colonization may vastly exceed the lifespan of a single civilization. The silence we perceive could reflect the natural limits of survival. Intelligent life may bloom brightly and briefly, leaving no lasting imprint on the cosmos detectable from afar. Another possibility is that advanced civilizations deliberately avoid detection. The universe may be teeming with life that has chosen stealth. Consider the motivations: survival in a potentially hostile universe, the preservation of resources, or the ethical choice not to interfere with developing civilizations. Such civilizations might exist in forms we cannot perceive, communicating through methods beyond our technological capabilities, or deliberately masking their presence. The silence could be intentional, a cosmic quiet imposed by intelligence itself. Time adds another layer to the paradox. The universe is 13.8 billion years old. Civilizations could have arisen, flourished, and disappeared long before our own species emerged. The window for contact might be brief in comparison to cosmic history. The radio signals, lasers, or other emissions we might detect could have passed by millions of years ago, leaving only the faintest imprint. In this sense, cosmic silence may not be absence, but misalignment, a temporal mismatch between civilization. Distance compounds the challenge. Even within our own galaxy, light travels at finite speed. The nearest potentially habitable exoplanets are tens to hundreds of light years away. Messages sent from intelligent beings would take decades, centuries, or millennia to reach us. Civilization lifetimes. The development of detectable technology and the speed of signal propagation may all conspire to maintain silence. The galaxy is vast, and even if life is abundant, contact may be effectively impossible for practical purposes. Cosmic evolution also suggests the possibility of self-limiting life. Advanced civilizations may harness energy efficiently, migrate to environments or modes of existence that are undetectable to us, or develop forms of communication we cannot yet recognize. Our instruments, our understanding, and even our assumptions about intelligence may constrain what we can observe. The universe might be alive with civilizations that are simply invisible to the narrow lens of our current perception. The Fermi paradox, in its starkest form, confronts us with existential questions about humanity. Are we rare, unique, or even the first of our kind in the galaxy? Are we latecomers to a universe that has seen countless cycles of emergence and extinction? The paradox forces us to confront both the possibility of cosmic solitude and the humility required to accept that our presence may be fragile and fleeting. The silence is not merely a challenge to technology, it is a mirror reflecting our own vulnerabilities and aspirations. The James Webb Space Telescope offers a new vantage in this exploration. By characterizing the atmospheres of distant exoplanets, it provides unprecedented insight into the conditions necessary for life. Spectroscopic analysis can reveal the presence of water, oxygen, methane, and other biosignatures. It can help us map the frequency and distribution of potentially habitable worlds, refining the probabilities that underpin the Fermi paradox. Each planet examined is a data point in the grand experiment of the universe, an opportunity to test assumptions about life's prevalence and diversity. Yet even as we gather this data, the paradox persists. Life may be abundant, yet technologically advanced life may remain elusive. We may discover microbial ecosystems on distant worlds, yet detect no evidence of intelligent species capable of interstellar communication. The universe may teem with simple life, while intelligence is exceedingly rare. Such a scenario would affirm the Fermi paradox in a new way. The cosmos may be full of life, but the silence of complex communicative civilizations endures. Alternatively, the discovery of life, or even biosignatures on a distant exoplanet, would reshape the paradox dramatically. A planet with a 99.7% probability of hosting life, as suggested by recent observations, would provide empirical evidence that life emerges readily under suitable conditions. It would force a reconsideration of the factors limiting intelligent life, shifting the focus from the emergence of life itself to the progression toward complexity and technological capability. The silence we observe could then reflect not the rarity of life, but the rarity of civilizations that survive long enough to communicate across interstellar distances. The paradox also illuminates the limits of human perception and cognition. We tend to frame the question of extraterrestrial life in anthropocentric terms. Intelligent species like us, broadcasting signals we can detect, inhabiting planets in ways we can recognize. Yet, the universe may host forms of intelligence, communication, or existence entirely alien to our expectations. Life could exist in forms beyond our sensory and technological reach, in environments far removed from our conception of habitability. The silence may reflect not absence, but the limitations of our imagination and our tools. Philosophically, the Fermi paradox invites reflection on the nature of observation, expectation, and meaning. The absence of detectable intelligence is itself a form of information, prompting us to refine our models, expand our curiosity, and consider alternatives beyond conventional paradigms. Silence is not a void, it is a signal demanding interpretation, It challenges us to explore the universe more deeply, to question assumptions, and to embrace uncertainty as an integral part of discovery. Moreover, the paradox fosters a deeper appreciation for the rarity and preciousness of life on Earth. If intelligent civilizations are indeed scarce, if survival is tenuous, then our stewardship of this planet gains new urgency. The silence of the cosmos becomes a reminder of responsibility to preserve life, to cultivate knowledge, and to ensure that the unique intelligence we possess endures. The cosmic quiet is not merely an observational puzzle. It is a call to conscious action. In revisiting the Fermi paradox, we also confront temporal, spatial, and existential scales simultaneously. The universe is both immense and ancient, yet our capacity to perceive and act within it is brief and limited. We are participants in a cosmic experiment, observers of phenomena that unfold over timescales and distances beyond intuitive comprehension. Silence may reflect the intrinsic difficulty of alignment between intelligent species across the vast expanse of space and time. The universe may not be empty, but the conditions for interaction may be extraordinarily rare. The paradox also intersects with notions of cosmic humility. Humanity is not guaranteed to encounter other intelligent life. We are not the inevitable culmination of universal processes. Our technological and cognitive abilities may be fleeting, our survival contingent on forces beyond our control. The silence of the cosmos is a mirror of both possibility and vulnerability, highlighting the extraordinary externalities that have allowed us to emerge, observe, and contemplate. Yet, within this silence lies inspiration. The challenge to detect and understand other civilizations fuels science, drives technological advancement, and expands human imagination. It motivates the deployment of telescopes like James Webb, radio observatories scanning the heavens, and theoretical models exploring the emergence, evolution, and distribution of life. Even in the absence of contact, the pursuit of knowledge itself becomes a form of cosmic engagement, a way of participating in the unfolding story of the universe. In practical terms, the Fermi paradox encourages methodological rigor. It compels scientists to consider biases in observation, the detectability of life, and the assumptions embedded in search strategies. Are we looking for radio signals because we understand them, or because we can measure them? Are we overlooking forms of communication, metabolism, or social organization that differ radically from our own? The paradox challenges not only our expectations but also our methods, urging us to expand both the scope and sophistication of our inquiry. The paradox also prompts reflection on time. Civilizations may rise and fall over millions of years, while human civilization has existed for mere millennia. Even if the galaxy has hosted thousands of intelligent species, the overlap of temporal windows for detection may be vanishingly small. Silence may thus be a consequence of timing, a universe in which intelligent life is common, yet rarely synchronized enough to make contact feasible. The absence of signals, then, is a product of cosmic timing rather than scarcity or design. As we refine our understanding of exoplanets, atmospheres, and potential biosignatures, the Fermi paradox evolves from abstract speculation to empirical question. Each discovery informs probabilities, constrains models, and guides hypotheses about the prevalence of life and the factors that govern the emergence of intelligence. A planet with compelling signs of habitability or life, observed by James Webb or future instruments, may recalibrate expectations, offering a data-driven framework to confront the silence and refine our understanding of cosmic evolution. Ultimately, the Fermi paradox is less a question with a single answer than a lens through which to explore the universe, ourselves, and the conditions for life. It exposes the fragility and contingency of intelligence, the challenges of survival, and the limitations of perception. It highlights the interplay of time, distance, probability, and context, revealing a cosmos both generous and indifferent. In grappling with this paradox, humanity is invited to reflect on its own resilience, creativity, and responsibility, to search more deeply, think more broadly, and embrace the wonder of existence within a vast and silent universe. Cosmic silence, then, is not emptiness. It is a call to inquiry, an invitation to humility, and a reminder that life, intelligence, and awareness are extraordinary phenomena in a universe governed by chance, time, and scale. Whether the silence persists because intelligent civilizations are rare, fleeting, undetectable, or simply misaligned with our temporal frame, it challenges us to refine our understanding, expand our tools, and cultivate the curiosity that drives discovery. In revisiting the Fermi paradox, we confront both the vastness of the cosmos and the singularity of our perspective. We are observers in a galaxy filled with stars and planets, potentially teeming with life we cannot yet perceive. The silence we encounter is a profound mystery, a canvas upon which the questions of existence, intelligence, and survival are projected. It is a silence that demands imagination, rigor, and wonder, inviting us to explore not only the cosmos, but our place within it. And in that exploration, we discover a truth that transcends any specific observation. The universe is simultaneously vast, ancient, and potentially full of life, yet profoundly inscrutable. The absence of detectable civilizations is not a limitation of the universe, but a challenge to human understanding. It calls us to develop sharper instruments, more expansive models, and more imaginative perspective. It reminds us that silence is itself informative, that even absence carries meaning, and that our quest to understand the cosmos is inseparable from the awareness of our own rarity and the potential for discovery. The Fermi paradox endures not because it is unsolvable, but because it is expansive, generative, and endlessly thought-provoking. It reframes every observation, every discovery, and every advance in our knowledge of the universe, from the identification of exoplanets to the detection of potential biosignatures. Each new piece of evidence engages with the paradox, refining the questions and illuminating the delicate interplay of chance, time, and complexity. The silence of the cosmos, paradoxical as it is, becomes a profound teacher of patience, of humility, and of the extraordinary significance of even the smallest flickers of life and intelligence within the vast, quiet expanse of space. Whether the universe is truly silent or merely beyond our current perception, the Fermi paradox compels us to look up, to listen, and to wonder. It invites us to consider not only the abundance of stars and planets, but the fragility, persistence, and potential of life itself. It is both challenge and inspiration, a reflection of the extraordinary probabilities and contingencies that have allowed humanity to arise, to observe, and to ask, in a cosmos so vast and ancient, are we alone? And in that question, the search for meaning, understanding, and connection continues, echoing across the silent stars. 14. Intelligence as a universal survival strategy. Intelligence is one of the most extraordinary phenomena to emerge in the known universe. From the earliest flickers of awareness in single-celled organisms to the complex cognitive architecture of humans, intelligence has proven itself to be an adaptive, transformative strategy for survival. It is more than a byproduct of evolution or a quirk of biology. It is a mechanism through which life negotiates complexity, uncertainty, and the relentless pressures of existence. When we contemplate intelligence in the context of the cosmos, especially in light of discoveries such as the James Webb Telescope's detection of potentially habitable exoplanets, we are invited to consider not only its biological and ecological significance, but its potential universality, a strategy that life may adopt wherever conditions are favorable. At its core, intelligence is about prediction and adaptation. Organisms with the ability to perceive their environment, anticipate changes, and respond flexibly enjoy a profound survival advantage. This is true on Earth, where animals capable of planning, learning, and social cooperation often outperform more physically dominant species. It is also likely true across the galaxy, wherever life evolves in environments of complexity, variability, and challenge. The capacity for foresight, problem-solving, and innovation could emerge as a natural strategy for survival. In this sense, intelligence is a tool for managing uncertainty, a way of transforming potential threats into opportunities and unknowns into structured knowledge. The evolution of intelligence is closely tied to environmental pressures. Life is rarely static. It exists in dynamic, often unpredictable conditions. Predation, climate variation, resource scarcity, and interspecies competition impose selective pressures that favor flexibility, creativity, and innovation. The brain, with its capacity to model the world, anticipate outcomes, and generate solutions, is a remarkable product of this evolutionary crucible. Intelligence allows organisms to navigate not only immediate challenges, but also long-term contingencies, storing knowledge, learning from experience, and transmitting culture and technology across generations. It is a survival strategy that scales temporally as well as spatially, extending influence beyond the constraints of immediate action. Across the cosmos, the pressures that shape intelligence may differ, but the principle remains consistent. Life that can anticipate and adapt will be more likely to endure. Consider an exoplanet orbiting a volatile star, where radiation flares, orbital eccentricity, or climatic instability pose existential threats. Life on such a planet may evolve sophisticated sensory mechanisms, predictive modeling, and cooperative strategies to survive. Intelligence, in this context, is not optional. It is a functional adaptation to environmental complexity. A planet with a 99.7% chance of life may not only host organisms, but could, in principle, give rise to forms of awareness capable of understanding and manipulating their environment. Intelligence is thus a cosmic solution to the problem of persistence. It allows life to negotiate conditions that simple, instinct-driven organisms cannot. Moreover, intelligence is intimately connected to energy. Cognitive capacity requires resources metabolic, environmental, and social. The development of intelligence often coincides with organisms accessing stable energy sources, maintaining environmental niches, and developing social structures. On Earth, the evolution of humans required not only biological adaptations, but also the capacity to exploit energy from food, fire, and eventually stored chemical and technological energy. Intelligence is therefore both a product of environmental opportunity and a means of amplifying resource utilization. In a universal sense, intelligent life is likely to arise where energy flows are sufficient to support sustained computation, information processing, and innovation. Intelligence is also a relational phenomenon. Its expression often relies on social interactions, cooperation, and communication. Species that can learn from each other, share knowledge, and develop culture create cumulative adaptive advantages. In human history, technological progress and societal resilience are deeply linked to collective intelligence. On an exoplanet with complex ecosystems, social cooperation could similarly enhance survival prospects, allowing species to mitigate environmental fluctuations, exploit resources efficiently, and navigate existential threats. Intelligence, therefore, is not just a feature of individual cognition, but a systemic property, amplified through networks, relationships, and shared understanding. From a cosmic perspective, intelligence also becomes a survival strategy at planetary and interstellar scales. Civilizations capable of understanding their environment, predicting planetary changes, and manipulating energy flows may avoid extinction from natural hazards, climate instability, or cosmic events such as asteroid impact. The emergence of technology, agriculture, metallurgy, energy production, and eventually space exploration is an extension of intelligence as a survival mechanism. It transforms organisms into agents capable of reshaping their environments, extending lifespans, and mitigating risk on scales far beyond biological instinct alone. In this light, intelligence is both adaptive and generative. It allows life to persist, evolve, and transcend the limitations of individual species or planetary conditions. Furthermore, intelligence facilitates abstraction, the capacity to conceive of time, space, causality, and morality. Conscious agents can model futures, reflect on past experiences, and anticipate consequences. This ability is crucial for long-term survival, allowing organisms to plan, strategize, and innovate in ways purely instinctive life cannot. On Earth, this has led to the creation of science, mathematics, and technology, tools that extend adaptive capabilities far beyond immediate perception. On other worlds, life that evolves intelligence may similarly develop abstract strategies to navigate environmental complexity, cultural dynamics, and survival challenges. Intelligence is not merely a biological trait, it is a framework for projecting survival across space and time. The universality of intelligence as a survival strategy also suggests that wherever life faces sustained challenges, selection pressures favoring cognitive complexity may emerge repeatedly. Life is adaptive by definition. It responds to constraints, exploits opportunities, and maximizes persistence. In stable, unchanging environments, intelligence may not confer a significant advantage, and life may remain simple. But in dynamic, uncertain, and competitive contexts, the evolution of complex cognition becomes a powerful adaptive strategy. On exoplanets discovered by instruments like James Webb, with atmospheres, climates, chemistries conducive to life, intelligence may arise independently as a natural consequence of environmental and evolutionary pressures. It may be one of the universe's recurring solutions to the challenge of persistence. Intelligence also serves as a buffer against existential threats. Whereas instinct and reflex govern immediate survival, foresight allows organisms to anticipate systemic risks and mitigate catastrophic outcomes. The development of tools, planning, and collective action transforms vulnerability into resilience. In human terms, intelligence has enabled us to build cities, develop medicine, cultivate food, and send spacecraft into space. On other worlds, the emergence of intelligence could similarly stabilize populations, manage ecological pressures, and extend the survival of species far beyond what purely biological adaptation would permit. Intelligence is therefore a cosmic mechanism for buffering life against both local and universal contingencies. In contemplating intelligence as a universal survival strategy, we must also consider its ethical and cultural dimensions. Conscious life capable of reflection may recognize the consequences of its actions, the limits of its resources, and the interdependence of ecosystems. Ethics, cooperation, and foresight become intertwined with survival. On Earth, societies that integrate knowledge, foresight, and collective responsibility tend to persist longer and navigate challenges more successfully. On alien worlds, intelligence may similarly give rise to cultures in which foresight, cooperation, and planning are not merely ethical ideals, but essential adaptive strategies. Intelligence is not only about information processing, it is about the conscious alignment of action with survival imperatives. Moreover, intelligence allows life to extend beyond its immediate environment. Through understanding and innovation, intelligent species can manipulate planetary systems, mitigate environmental hazards, and even consider interstellar migration. The capacity to conceptualize space, time, and energy flows transforms intelligence into a mechanism for cosmic survival. Whereas simpler life forms are bound to local conditions, intelligent life can project influence, anticipate challenges, and develop contingencies that transcend the limits of a single planet. Intelligence becomes a bridge between travel and exploration, between persistence and expansion. Intelligence is also intimately connected to information. The capacity to acquire, store, process, and transmit knowledge is central to adaptive success. On Earth, this manifests in DNA, neural networks, language, and technology. Across the cosmos, information processing may be a hallmark of life-seeking longevity. Species that can integrate experience, model complex systems, and communicate effectively gain a disproportionate advantage. In this sense, intelligence is a strategy not only for immediate adaptation, but for cumulative resilience, the ability to learn, iterate, and optimize survival across generations. Consider the interplay between intelligence and environmental stewardship. Species that recognize causal relationships between actions and long-term consequences can actively shape their environment to enhance survival prospects. Agriculture, conservation, resource management, and technological innovation all exemplify intelligence guiding adaptation at scales beyond the individual. On exoplanets, intelligent life may similarly learn to regulate ecosystems, anticipate climate variation, and navigate planetary hazards. Intelligence transforms vulnerability into agency, allowing life to persist in contexts that would overwhelm simpler organisms. The universality of intelligence, as a survival strategy, also implies that wherever life develops, there may be convergent pressures favoring similar solutions. Across distant star systems, planets with comparable conditions, energy availability, chemical diversity, environmental complexity may independently give rise to intelligence. The underlying principle is consistent. Environments that reward prediction, flexibility, and innovation will select for cognitive complexity. Intelligence is therefore not merely a local anomaly, but a plausible recurring adaptation, a strategy life uses to navigate uncertainty wherever it arises. Intelligence also transforms temporality. Conscious agents are capable of planning across decades, centuries, and millennia. They can preserve knowledge, anticipate trends, and take proactive measures to enhance resilience. On cosmic scales, this ability allows species to mitigate stochastic risks, respond to environmental flux, and potentially engage in interstellar exploration. Intelligence expands the horizon of survival, connecting the present with future contingencies in ways that purely reactive life cannot. It is a temporal strategy as much as a biological one. Furthermore, intelligence may facilitate technological transcendence. The emergence of tools, energy manipulation, and eventually spacefaring capability is a natural extension of the survival imperative. Civilizations capable of harnessing energy efficiently protect themselves from existential threats and explore beyond their planetary cradle, increase their chances of persistence exponentially. Intelligence becomes a pathway from local adaptation to cosmic resilience, enabling life to survive not merely for generations, but potentially for eons. Yet, intelligence is not without risk. Cognitive complexity introduces vulnerability, over-reliance on technology, ethical missteps, and unforeseen consequences can threaten survival. This duality underscores intelligence as an adaptive strategy that requires wisdom, foresight, and social cohesion to succeed. Survival is not guaranteed by intelligence alone. It is realized through the careful application of knowledge, planning, and cooperative action. Across the cosmos, civilizations may fail, not because intelligence is absent, but because it is misaligned with sustainability. From the perspective of the James Webb discoveries, intelligence takes on new significance. When we detect planets with high probabilities of habitability, we are glimpsing the potential stages of life that might eventually develop awareness, problem-solving capacities, and perhaps technology. Intelligence is not merely an earthbound phenomenon. It is a possible trajectory of life wherever conditions are conducive. It is a cosmic strategy embedded in the interplay of energy, information, and environmental challenge, a universal solution for persistence in a universe governed by entropy and chance. Intelligence is also a bridge to meaning. Beyond survival, conscious life seeks to understand its context, to interpret the universe, and to act purposefully. The emergence of intelligence allows life to reflect on its own existence, to anticipate threats, and to create strategies that extend far beyond instinctual survival. In this sense, intelligence is both practical and existential. It ensures persistence while enabling comprehension, transformation, and the projection of agency into realms that would otherwise remain inaccessible. Ultimately, intelligence, as a universal survival strategy, demonstrates the interplay between biology, environment, and cosmology. It is an emergent property of life navigating uncertainty, complexity, and scarcity. It amplifies adaptability, extends temporal reach, and allows for the conscious shaping of destiny. Across the galaxy, wherever life faces challenges, intelligence is likely to confer a profound advantage, not guaranteed but favored, tested, and refined by the pressures of existence. In reflecting on intelligence, we recognize it as one of the universe's most remarkable adaptive tools. It is both a product of evolution and a principle with potential universality, a mechanism by which life persists, thrives, and navigates the cosmos. It is the intersection of awareness, information, and strategy, allowing life to transcend immediate limitations confront contingency, and envision futures. On distant exoplanets, within the swirling gases of nebulae, or along the surfaces of worlds bathed in alien suns, intelligence may arise again and again, a recurring solution to the universal problem of survival. Intelligence, therefore, is not merely a characteristic of Earth's life. It is a principle that may recur wherever life encounters complexity and challenge. It is a cosmic adaptation, a strategy honed not by design but by necessity. It is life's most sophisticated tool, enabling anticipation, innovation, cooperation, and transformation. Across the universe, wherever the conditions for persistence intersect with variability and opportunity, intelligence may emerge as the natural and inevitable response, a testament to the capacity of life to endure, adapt, and engage with the infinite possibilities of the cosmos. It is in this light that the discoveries of instruments like the James Webb Telescope take on profound significance. The identification of planets with a high probability of life is not only a testament to the abundance of habitable environments, but a glimpse into the potential for intelligence to arise elsewhere. Life, given the right conditions, may once again discover strategies of awareness, adaptation, and persistence. Intelligence is the universe's answer to uncertainty, a strategy for survival that transcends species, planets, and even epoch. In contemplating intelligence as a universal survival strategy, we are invited to see ourselves as part of a continuum, a lineage of conscious life that may find echoes across the stars, shaped by the same cosmic imperatives, guided by the same fundamental pressures, and inspired by the same drive to endure.